Okay, it says we're live here. Chris, do you know, can we switch this from tile view? Actually, no, I think it's set up right. Yeah, when someone's presenting, then it'll flip. Okay, test on the live stream. Cool, looks good. I hear it back, play back on my phone here. Nice. Thanks, Renato. Confirming that the live stream looks good. That's a cat wandering around in the background. Amorphous blob. Cool. I guess we'll get started then. Okay, so hi everyone and welcome to the first ever LLVM Distributors Conference. My name is Nixpkgs. I'm the Linux kernel co-maintainer for LLVM support, and I work on Android's LLVM team at Google. You may know me or have seen me reverting your patches upstream due to breaking kernel builds. If you need to reach me at any point during this conference, I'm on LLVM's Discord and my IRC handle is Ndizone, but good luck spelling that. If you found this conference useful, maybe you could buy me a beer sometime. Some quick thank yous. Thank you all for attending, including future viewers of the stream. Thanks Google and YouTube for the infrastructure we're running on, and thanks particularly to Christopher Truong and Brittany Lamonto for helping set up the live stream today. Thanks for the support of the LLVM Foundation. The next developer meeting will be online November 17th to the 19th. Get your CFPs in for that deadline. It's coming up in 4 days, September 20th. And please make sure to hold all questions for the speakers. To maximize content throughput, we've asked all speakers to stick to strict 15-minute presentations. The schedule is on GitHub. We'll generally be having 4 15-minute talks followed by a 15-minute break with a 30-minute break for lunch. Please ask speakers questions in their respective CFP issue on the GitHub. We may have time for questions at the very end of all presentations, which I can take from the YouTube live chat. We plan on having recordings available sometimes afterwards. Make sure to subscribe to the LLVM YouTube channel. So why have a distinct conference focused on the distribution or release engineering aspect of a compiler? Well, I have to admit, I found myself a little disenfranchised or perhaps disengaged from the usual conference talks. Yet another talk about global ICEL, loop optimizations, a new meta compiler infrastructure. Look, I don't have a PhD in compilers. Those talks and the work they describe are important. They do and they will benefit many users. They're deep technical subjects, and someone needs to pursue them. But I can only look from afar with minimal understanding before I have to get back to shoveling coal into the boiler. I mean, sometimes it feels like half this job is just trying to ram a literal ton of code of varying quality through the latest version of the compiler, while the other half is helping triage bizarro failures because, as we all know, it must be the compiler's fault. And really, between those two, there's not always a lot of time spent actually adding new optimizations to the compiler. This doesn't always feel like a step forward, maybe a step in a direction, but maybe not always the direction that you intended. And surely I can't be the only person that feels this way. So if any of this resonated with you, then this conference really is for you. Major strengths of LLVM include all of the diverse ways it's used in many different projects, its large community of contributors, and its multiple corporate sponsors. Hopefully today is a showcase of that, and maybe next time we can get even more speakers from additional organizations to further demonstrate that. Hopefully this helps you find existing solutions to problems you actually have, or at least introduces you to people with similar difficulties or relevant expertise. And finally, if you're a salty boy like me, I hope this shared commiseration session grants you some form of catharsis. Thanks again, and take it away, Peter.
Okay, thank you, Nick. Thank you for organizing this conference. I'm really looking forward to the content. So my name is Peter. I work at Google, and I lead the Fuchsia Toolchain team. In this talk, I'm not going to be talking about Fuchsia Toolchain build. I'm going to be talking about something slightly more generic, which is the LLVM Runtimes build. So let's start off with a little bit of a background. So throughout the day, you're going to hear the word toolchain a lot. And whenever we talk about toolchains, people, like the first thing that pops up in your head is a compiler. And compiler is a really important part of your toolchain, but it's not the only part of the toolchain, right? In order to build a functioning program, we need lots of other pieces. We need assemblers, we need linkers, we need archivers, other debugging diagnostic tools. We also need compiler runtimes. These are libraries that will typically be shipped with your toolchain and are going to be used by the compiler. There are compiler runtimes, which contain built-in functions the compiler may generate out calls into. There's going to be your C standard library, your unwinder, your API library, your C++ standard library, and potentially many more. There might be sanitized runtimes, you might have OpenMP runtimes, and so on. Now, whereas building the tools themselves is usually pretty straightforward. You just run CMake. Building runtimes can be pretty challenging, as many of you probably already know. In practice, I've seen 3 different ways generally to build these LLVM runtimes. First off is the external build. The second one is the LLVM projects build, and the third one is the runtimes build. So let's look into those in a bit more detail. So what do I mean by external build? Well, this means that you invoke, you build each runtime separately by invoking respective CMake builds in each runtime project. And then you have some custom scripts or external build system to drive and orchestrate the whole process. This gives you a lot of flexibility. Like, you can really order things in a way you want. You can insert additional steps. You can even build things that are not part of LLVM throughout this process. But that flexibility comes with a little bit of a cost, right? If you, for example, look at Android or Chromium, which is what I've included some canonical example of this approach, you would see that they do a lot of the same logic in their build scripts, but they don't really share any code. So, there's usually going to be some amount of duplication when you are using this approach. Another alternative is the LLVM projects build, which is sort of the classic way of building LLVM, or the default way of building LLVM, at least today. And it's what most of you are probably familiar with. It simply means listing all your projects and all your runtimes in the LLVM enabled projects list. And in this case, what it means is that all your runtimes, your unwinder, your C++ library, are going to be built as part of the LLVM build using the host compiler. It's very simple, it's fast and straightforward, and it can be also very dangerous, right? The problem is that your runtimes, as I mentioned, are going to be built using your host compiler. So say if your host compiler is GCC, they're going to be built with GCC, but then they are going to be used with Clang that you've built that is for your toolchain. And there is no guarantee really that GCC and Clang are going to use the same API. That runtimes built with one compiler are going to work with the other compiler. I mean, you may be lucky, but there may not. I mean, there are ways around it if you understand the problems, right? You can, for example, use multi-stage builds to make sure that your host compiler is same as your target compiler, but it's going to be pretty difficult. And I don't think that everyone using this approach is even familiar with all the potential risks. So that's why we have LLVM runtimes built. This is a newer, more modern way of building LLVM runtimes. It uses a slightly different variable. Instead of enabled projects, we have enabled runtimes. And in this case, the runtimes will be built as part of the LLVM build, but they're going to be built using the just build compiler. So we're basically going to take the build and we're going to split it up into 2 phases. In a first phase, we're going to build your compiler and all the other tools. And then in a second phase, which is going to be a separate child CMake invocation, we're going to build all the runtimes using the just build compiler. This guarantees that the API between the compiler and runtime is going to be correct, but the use of a secondary CMake build introduces some additional overhead, which is the biggest cost when using runtimes build. How do you use it? It's really straightforward. In the traditional projects build that you're probably already using, you just say LLVM enable projects equals Clang, LLD, libc++, whatever else you need. In the runtimes build, you split this up. You still put your tools, projects that you want to build with the host compiler into the enable projects variable, but then you take all the runtimes and you're going to put them into the separate variable. And really, that's it. I mean, we could just end here and, you can go on and play with it and hopefully you will enjoy it. But the runtimes build is more powerful than this. And I hope I could spend the rest of my time actually talking about some of the more advanced features that you may want to take advantage of if you decide to use Runtimes build. So first up is the support for multiple targets, which I think is really the most exciting and powerful features. So Clang is cross-compiler, which means that it can target like multiple architectures and operating systems without needing a different compiler binary. But that means that you also need your runtime libraries for those different targets. For each target you want to support, you will need a separate build of those libraries. Now, this is not something that you can do easily with the projects build because we're always targeting just one target, the default one. It is possible to do with external build, but Runtimes build can do it easily because, like I already mentioned, we have those two phases. We have the second stage where we build Runtimes with just build compiler. And so all we have to do is we can just invoke CMake multiple times, once for each target that you want to compile Runtimes for, and that's really it. And that way you can cross-compile Runtimes for many targets and even do multi-list, which is something we're going to touch on later. Each target has a separate child CMake build with its own set of flags so they don't collide. To use it, all you have to do is you set your targets in the LLVM built-in targets variable. We also have a way to pass flags to each target build by using a special prefix. You need to do this separately for built-ins and for runtimes. Now, in these code examples, I'm using the CMake syntax. This is code that you would typically put into your cache file, like the one that we use for Fuchsia, which you can check out in the LLVM repo. But you can also pass these on a command line. It absolutely works. It just may become a little bit more complicated when you have lots of these. Why do we need to do built-ins and runtime separately? It's the bootstrap ordering issue. The problem is that when you are building all the runtimes, you first need to run CMake, and CMake is going to run a whole bunch of checks to see if your compiler is working, if your compiler supports all the right flags. And those checks in CMake typically assume that your compiler is at least somewhat functional. And somewhat functional typically means that your compiler RT built-ins are usable. And in order to ensure that, we actually have to build built-ins separately just before. So when I said that there are two CMake builds, there's the one that you use to build all the host tools, and then there's a second one to build your runtimes. That wasn't actually the full story. There are in fact three CMake builds. There's one build to build host tools, and then there's a child CMake build to build your built-ins followed by runtimes. And then you need to repeat that for every target that you want. So if I want to build my runtimes for 2 different targets, as is this example that's shown here, there are going to be 5 CMake builds. Now, this is still all managed by CMake and by runtimes build for you. So in practice, you don't really need to, you're never going to encounter this unless you decide to dig into the build internals. But it's something to be aware of, and it is where some of the overhead comes from. Now, in here, it's shown how it's going to look like, like what you're going to observe. Now, the 2 targets shown here, which is the AR64 Fuchsia and x86 Fuchsia, could be in theory built in parallel. In practice, that's not really like possible because when we have these CMake child builds, we want for those to have access to terminal, so you can actually see the output as the build is running. And because there is just one terminal, that's what is basically serializing the execution. The other useful feature that might be we're talking about is multi-libs. Multi-libs basically means that you can have multiple versions of the same library on the same target. Right. This is useful. Traditionally, this has been used in embedded world when you wanted to have the same runtime library compiled, for example, for hard float and soft float. But even if you're not doing embedded, this can be super useful. For example, we use it to have C++ runtime library compiled with sanitizer instrumentation, with and without exceptions. you can come up with a lot of creative ways to use this. And the multi-lib super is built in straight into Runtimes build. So if you want to use it, it's really straightforward. There is a separate variable for that, just like before. So there's the LLVM runtime multi-libs, where you list names of your multi-libs. You can configure which targets to use that multi-lib for. And then you can, again, use the special prefix syntax to pass any additional flags you need to each of those multi-lib builds. Now, something to keep in mind is this can get expensive pretty quickly, right? Imagine that I have 2 operating system targets, I have 2 architectures, I have 2 multi-libs for each target. Now, if you multiply all that, suddenly you're talking about lots of CMake builds, so it can take quite a bit of time. So be careful when you start using these a lot. The last thing I think is worth talking about is the per target runtime layout. So traditionally, in the old LLVM layout, there will be just one, like a default location where your runtimes are going to be installed. So for example, libc++ is going to go into lib/libc++.a or .so. Now there's a problem if you start compiling runtimes for multiple targets, because like where are you going to put those, right? So in order to enable installing runtimes for multiple targets side by side, we need to somehow segregate them. And the way we do this is we use what is known as the multi-arch layout, and that's controlled by the enable per target runtime variable, which is a mouthful, but we're working on making it the default. So hopefully we don't have to know about these soon. And whereas in the projects build, at the moment, it's still something you have to turn on manually. In Runtimes build is enabled by default. And in practice, what this simply means is that anytime you're building like runtimes, we're going to create a dedicated directory for all the files related to those runtimes for each of your targets. So in here, you can see example, like we're going to have a dedicated directory for headers, for built-ins, and for other runtimes like libc++. And if you decide to use multilib, there's also going to be a dedicated subdirectory for each multilib. And again, this is following a standard layout that's already used on other platforms. So that's really it. Like these are what I would consider most important and useful feature of the runtimes build. There's still plenty that could be improved. I've already some of the ideas that we have and that we've been talking about here. I'm probably not going to go into detail of every single one of them, because this is probably only going to be interested for people who really enjoy digging into CMake internals. But to summarize, basically all of these are somehow related to reducing the amount of duplication across different child CMake builds, and maybe even cutting down the number of child CMake builds. So for example, I believe that there might be a way to actually avoid having to have a separate CMake child build for built-ins and for runtimes with a little bit of work. We might be actually able to combine those, so that might cut out the number of CMake builds that we have flying around quite a bit. And there are other ideas how we can reduce the overhead even more. So to summarize, I've talked about 3 different ways of building LLVM runtimes. There's the external build, which is really flexible, but can be complicated. There might be a lot of duplication across projects that use these. There's the projects build, which is still the default. It's simple, fast, but also limited and potentially dangerous. And then there's the runtimes build, which is what I would consider modern way of building LLVM toolchains. It's I believe simple to use. It's quite powerful, and we hope that it's going to become the standard way of building runtimes in the future. So if you haven't already done so, please give it a try, see if it works for you. If not, we're interested in hearing from you. Send us your feedback, file bugs, and yeah, I hope it's going to work for you. If you have any questions, please post them to the issue that's to the issue for this talk, and I'll try to answer all of those. And if these kind of topics are interested to you, and it is something that maybe you would want to work on as your full-time job, I'm also going to mention that our team is looking for engineers that like to work on problems like these. So if you're interested, please reach out to me. And thank you.
Great. Thank you so much, Peter. That was a fantastic talk. Okay, next up, we're going to hear from Alessandro and Filippo from rev.ng.
Yeah, you can hear me, right?
Sounds good.
All right, so just 1 second. I will share my screen as well. You should be able to see it now.
Looks good.
All right. So yeah, thanks for having me. I'll spend a couple of words about myself. I'm Filippo Cremonese, and I work at rev.ng. We are a small company with expertise in compilers, emulation, binary analysis, and binary translation. And we are currently building our binary analysis framework, complete with a decompiler, which is based on QEMU and also LLVM, and that's why I'm talking at this conference. Right. If you're interested in checking out our work, you can apply for the beta at rev.ng, and I'll get straight into my talk. So I will briefly touch upon those points, namely the usage that we do of LLVM at rev.ng and why we are also distributors for LLVM, the tool that we built to address our needs, which we call Orchestra. And also I will touch about a bit on our adventures in cross-compiling LLVM for Windows on Linux, and about our set of patches that we maintain for LLVM with focus on the build system, the patches that we apply to the build system of LLVM, and a couple of pain points that we have addressed, that we had to address while building and distributing LLVM. So as at rev.ng, we are in a peculiar position where we are both LLVM distributors and LLVM developers. And in fact, we do ship multiple LLVM, what we call components. The first of them being what we call Clang release, which is actually a stock version of LLVM, which we use as a compiler, as our main tool chain for building all our projects. And then we ship what we call our LLVM component, which is our customized version of LLVM with our patches, which makes it suited for our needs. The last component, LLVM related component that we ship is actually LLVM documentation, which is Doxygen, the Doxygen generated documentations ready to use in Zeal or Dash. I guess many of you will have heard of or used them. So yeah, as distributors, we have some wishes, and the main ones are that we want to be able to have a self-contained and portable install root. So to be able to install the software that we build without root privileges, and to be able to move the binaries that we produce around the file system and have them working flawlessly. And we also want to produce binaries that work across different distros, and also on distros which are older than the distro on which we are building on. We also want to have a way to easily set up cross-compilation toolchains, which are famously, I guess, hard to get right. And we want a system that is CI-friendly. Whereas as developers, we want to be able to provide an easy and quick way to set up our development environment, which is not tied to a specific distro. In fact, our developers at rev.ng are free to choose whatever distro, Linux distro they want, as long as it's not like completely ancient. And also, we want to provide them with a uniform environment, so with modern tool chains and with the same tooling for all developers. And this also enables them to reproduce bugs more consistently, since everyone has the same compiler, everyone uses the same build scripts for building all the software that we use. And the last thing, we also want to enable our developers to build from source only the components that they strictly need to build from source. And to address those needs, we built Orchestra. Orchestra, we use it to fetch, configure, and build all the software components that we need. We currently have around 150. They are, however, heavily templated. And Orchestra is able to provide us with the movable installation route, thanks mainly to our path magic. And it also allows us to build on one machine, on one distro, and have the binaries work on older distros by linking against a legacy, very, very old glibc. Orchestra also supports what we call binary archives, so which are built by the CI. So if one developer wants to install a software project without modifying its source or its build scripts, it can do so from pre-built binary archives, and this saves a lot of time, especially when we're talking about projects as big as LLVM, which can take a lot of time to build. And another thing that Orchestra supports, which I find very, very handy, is multiple interchangeable bit flavors. So our developers are able to install, for instance, LLVM in debug mode without optimizations, or with debug symbols, but with optimizations on, or in release mode, so fully optimized and completely stripped. And also there are ASIN versions of all the previous all the previous things that I mentioned. If you're interested in Orchestra, to check it out, it's open source. You can go on our GitHub space and uses a YAML configuration syntax and YTT for templating. I will not talk more about Orchestra, but please get in touch if you're interested in that. So as I mentioned, the next thing I want to talk about is our adventures in cross-compiling LLVM for Windows. So the high-level steps for them are, one would say, pretty obvious maybe. The first one is you have to have a cross toolchain. For that we use Min-GW, and we use it to get a GCC and libstd C++ cross toolchain which works on Linux and is able to produce Windows executables. And we found that we had to configure it with pthread support. I will not get into detail about how we managed to do it. It's not as straightforward as it could be, but it will be off topic. And then the next obvious, like high-level steps is you use that cross toolchain to build LLVM and then libc++, and libc++ ABI. Now, for what concerns cross-compiling LLVM for Windows, the process was pretty straightforward, not completely, however. We found that we had to make some patches to some of the LLVM CMake files, and those were mostly solving some link problems. So, for instance, there were some missing libraries to some link targets, and we also found that we had to add a custom toolchain file to be able to allow CMake to build the host tools which are used by the host at build time to auto-generate some files. An example of those would be LLVM TableGen and Clang TableGen. Lastly, one of the biggest problems that we had to solve was an obscure linking problem, which we solved by using LLD. We found that using LLD was basically necessary to be able to cross-compile LLVM for Windows, because LD BFD spins for a couple minutes, then it prints an error, and then it gets stuck for another 2 or 3 minutes before exiting. The root cause for this, it turns out, is that some DLLs, namely Clang AST, but probably also others, fail linking because they export more than 2 to the 16th power symbols, and that's apparently hard limit in some build processes for Conf executables. So that's that. Where cross-compiling LLVM for Windows was still pretty straightforward, the same cannot exactly be said for libc++ ABI and libc++. So we had to manage to cross-compile those for Windows. We sat down and had to do some iterative debugging sessions for the build process, and it led us to some incantations, some flags that we had to specify. I will not get into details for each and every one of those. The reason I am speaking about them is that we think that some of them can be fixed to improve the quality of life for ourselves and probably for others that may want to cross-compile LLVM for Windows on Linux. For instance, one of them is one of the things that we think can be improved is that for libc++ ABI, we needed to tell it where to find the headers for libc++, and also vice versa. We needed to tell where the libc++ ABI headers were for libc++. We're not entirely sure why this is needed, at least for monorepo builds, and we think this can be fixed upstream. Also, there were other flags which we needed to set, and one was particularly puzzling, namely libc++ C++ ABI enable new delete definitions, which we found that apparently has to be turned on either in libc++ or libc++ ABI. We're not entirely sure why. And there were a couple of other flags which needed to be set and were not auto-detected where we think they should be. For instance, the flags which tell CMake that there is support for Win32 thread APIs. A very similar thing applies for libc++. If you are interested in checking out the flags that we used and the ways that we managed to compile libc++ ABI, libc++ and LLVM for Windows, you can check out branch feature Windows on our GitHub projects, LLVM project and Orchestra. So there's that. The next thing I want to touch on is our LLVM fork, which we maintain. It's a fork with some commits, which we needed to make to tailor LLVM to our needs. And we try not to diverge too heavily from upstream. And the way we do it is we rebase on each LLVM release, but we do not rebase on trunk. We do, however, backward some improvements on a per need basis. Some commits we cherry pick from upstream where we found that they are useful to us. One of the things that we fixed is the ability to build LLVM using C++20. We tried to build our projects using the most recent version of C++ available. And so we found that to be able to build LLVM using C++20 version of the standard, we needed to fix some compatibility between string ref and UTF-8 string leaders, and also some usages of comparison operators, which were ambiguous, but nothing too bad, really. And we also do maintain some MISC patches, which I mentioned because we think that they might be of interest to the community at large. So an example of those would be we implemented zero copy filters for graph traits, which allow you to filter big graphs without doing expensive copy operations. We also made some improvements to SROA to allow more aggressive low speculation across multiple fees and select instructions. And we applied also a patch to lazy value info to better handle masked values and the built-in CTLZ call. So if there's interest in the community, please get in touch. We are very interested in upstreaming those. And also the patches to CMake, which help with cross-building LLVM. The last thing I want to get into is some pain points which we had to address while building and distributing LLVM. The first one of those concerns ndebug. Ndebug is a macro definition that LLVM uses to determine if it's being built in debug mode or not. And the problem we have with that is that some structural classes in public headers change their layout, for instance, have or don't have members depending on the value of ndebug. This is a problem because if we build LLVM, for instance, in debug mode, and then we have a project of ours which uses LLVM public headers, which is built without the ndebug macro defined the same way as the one in which LLVM was built, this is a problem because they're not using the same ABI. And by the way, a similar issue, basically the same issue emerges when building with or without other sanitizer. The way we are solving this at the moment is definitely not ideal. We basically replace ndebug with a fixed value at LLVM build time. So we ship headers which have this ndebug replaced with a fixed value. The proper way to solve this would be to basically not use, or at least not have structures, public structures, which change their layout depending on the value of ndebug. Then we found another minor thing, that a test is failing if you're building as root, and this is the case for us in our CI, at least. because being root bypasses some permission checks. This might be already known upstream to LLVM. We're not sure about this. It for sure is, at least for Gentoo, we found that someone reported this. So it's another thing that can be improved about LLVM. And I have another 2 more pain points, and then I'm done, I promise. This is not supposed to be a rant. The first one is that LLVM config -- version shows the Git remote. This is a problem. This was a problem for us because we use GitLab CI, and GitLab CI provides the build system with an HTTP remote, and that includes username and password. So we found that when LLVM config -- version was being invoked, it was leaking credentials for repos in the CI logs. Our solution for this, again, not completely ideal. We patched CMake to ignore if the source is a Git repository. A proper solution, of course, would be to patch LLVM config to redact that information, or possibly to do so in the CMake if that's a saner way to do it. A last thing, not strictly build related, that we found, not strictly related to building LLVM itself, but more to distributing it, is that we found it's not possible to load multiple versions of LLVM in the same process. We needed to do it because our UI uses Mesa, and Mesa uses LLVM, but we also do use LLVM in Revenge, and this is a problem because we solved it by compiling Mesa again and linking Mesa against our customized version of LLVM. This is less than ideal because it also means that we have to ship Mesa, which we really don't want to do if possible. And so we are working towards this better solution, also from a software engineering standpoint, one might argue, which is separating the decompiler engine from the UI process. But if there's interest from the community, again, we think that it might be something worth discussing if loading multiple versions of LLVM in the same address space is useful or not. We might be interested in working towards that. So that was it. Thank you for listening. If you have questions, you can post it on the LLVM Distributors Conference issues list on GitHub. And if you want to get in touch, feel free to get in touch via email or on Twitter at fgremo or at Revenge. Thank you very much.
Wow, thank you so much, Filippo and Revenge. A lot of interesting challenges faced there. Okay, next up, we're going to hear from Salim, who's going to tell us more about Swift on Windows. Salim's a Googler, but I believe this is a personal project, if I understand correctly. Salim, you ready to go?
I believe so. Just a moment. Right. Is it presenting?
Yeah, looks great.
Great. All right. Thanks a lot. And yes, this is a personal project. Right. So hi, I'm Salim. I'm a software engineer at Google and a longtime LLVM contributor turned distributor. I'm going to cover some of the design choices that went into the Windows Swift distribution. Along the way, we will discover some interesting problems that the projects create for the distributors, particularly for a non-commercial undertaking. For anyone who is not yet familiar with Swift, allow me to give a brief description. Swift is a modern language with module system, support for concurrency, value immutability, type inference, a package management system, etc. It is a type-safe language using static typing, providing value type semantics, automatic reference counting or ARC, preferring optionals over a nil type, amongst others. Swift is a multi-paradigm language, enabling imperative, functional, generic, and other programming styles. Primarily a general-purpose programming language, affordances for DSLs aid in fitting into certain domains. Although it is most often used for application programming, it is designed to be usable for systems programming. There are examples such as the system and numerics packages, which do show Swift in those domains. Those involved in the LLVM community may be thinking, great, you have a compiler. How does that relate to LLVM distributions? The Swift toolchain is LLVM-based. It incorporates the LLVM, Clang, LLD, and compiler RT subprojects. Furthermore, the Swift toolchain integrates support for multiple languages beyond just Swift, such as C, C++, and Objective-C. The distributed toolchain is meant to be used as a complete toolchain. It includes the compiler, assembler, linker, and debugger. Oh, and there's one more thing. Swift has integrated FFI. What does that mean? This module system extends past Swift and into C. There's active development to also enable C++ interop. This feature enables natively binding C and C++ declarations into Swift, allowing Swift code to call directly into foreign code. PythonKit draws inspiration from this and even bridges Python right into Swift. The FFI is compile time. That is, the FFI is emitted inline as native code. This is done by embedding a copy of Clang into the Swift frontend and generating the foreign call as a regular function call. The FFI support is based on Clang modules, the original module system that was added back in 2013 and would eventually grow into Clang C++ module system. With Swift targeting a variety of platforms and using an LLVM-based toolchain, it should be no surprise that the Windows Swift toolchain is set up for cross-compilation. Swift eschews the traditional C compilation model of a translation unit at a time for a module at a time model. This requires a larger address space, and as such, currently the Windows toolchain is only available for 64-bit hosts. The resulting toolchain can target Windows, Android, Linux, and WASI across a variety of architectures. Swift on Windows was ported as a non-commercial effort. The effort started nearly 5 years ago before GitHub Actions. Fortunately, Microsoft provided an amazing service, Azure Pipelines. This service provided free Windows builders for open source projects. However, building a toolchain is not a small feat. Cloning the sources on the builder takes about 30 minutes due to the LLVM monorepo. The build artifacts for release build without debug information are approximately 10 gigabytes. Adding debug information bumps that to 50 gigabytes. Comparatively, the SDK portion of the distribution is about 500 megabytes for a build with debug information, and the developer tools weigh in at about 200 megabytes. A build of the x64 toolchain takes roughly 8 hours to build on Azure Pipelines. This is a single-stage, non-LTO, non-PGO build of the toolchain. The distribution is packaged into a set of MSIs and an installer executable. The installer is about 500 megabytes, and when installed, it takes about 3 gigabytes of disk space. Because terminology can be confusing, let's walk through the components. The toolchain would be the first subcomponent. This is the C, C++, Swift compiler drivers and frontends, the assembler. The distribution uses the LLVM integrated assembler, linker, the distribution bundles LLD, and debugger, LLDB. But we also need the supporting tools that one expects, often dubbed binutils, so add on the name tool, objdump, undecoration tool, etc. Since we target Windows in addition to Unix platforms, we need the Windows tooling as well, things like the manifest tool and resource compiler. The SDK is a Swift standard library, which also includes the Swift language runtime, and support libraries and a testing framework. The developer tools are the supplementary tools which developers need to be productive: package manager, code completion, indexing tools, and a Swift LSP. Due to builder constraints, the build must be orchestrated as a series of phases. The complete distribution has over 32 individual builds that ripple through. For the first phase, we build the C, C++, and Swift compilers and package up some dependencies. This feeds into the second stage, which builds the SDKs for the various platforms and architectures. Simultaneously, we can package up the MSIs for the toolchain. The next stage builds the developer tools and packages the SDKs for installation. Then we drain the pipeline, packaging up the developer tools. Finally, all the MSIs can be bundled together to form the installer. The astute observer would likely have their eyes drawn to the bottom center block of MSIs being shown. That certainly looks like a very large number of MSIs. Well, we have 2 platforms and 4 architectures per platform. From those, we generate 2 components each, the runtime redistributable and the development SDK. So really, we have 16 different packages to build for the SDKs alone. This separation permits us to simplify the redistribution of the runtime libraries with applications. The runtime MSI can be repackaged with Swift applications. The SDK component is a developer-only portion of the SDK. The Swift interface definitions and the linking component import libraries on Windows. For non-Darwin targets, this can either be a copy of the runtime library, which is unnecessarily large, or IFSOs, interface libraries. Check out the Clang interface library lightning talk by Puyan Lotfi from the 2019 LLVM developer meeting for more details on that. Pulling together some of the previous crumbs, Swift natively interoperates with C and C++, and the SDK only has Swift and its support libraries. The reason for this is that the C and C++ portions of the SDK are meant to be provided by the system. For Windows, this is a Windows SDK that Microsoft distributes, and for Android, that is the NDK. These cannot be redistributed, and we require the user to provide them. The Windows SDK is interesting that it is not standalone, but has an implicit dependency on the MSVC toolset. This is bizarre in this case, because we do not even use the MSVC compiler. As it turns out, the MSVC toolset provides some of the runtime headers that are not available standalone. Explicit modules requires a module map definition, which needs to be placed alongside the headers, as there is no guaranteed absolute path that we can use for the module map definition. The user must install the module maps, though this can be automated through MSI custom actions, custom C++ code. However, the module maps for a third-party package must be maintained in a forwards-backwards compatible manner without involvement from the owner still. The Windows Swift toolchain ignores one of the important rules of packaging: follow the system's rules. Instead, it prefers to be somewhat more similar across platforms. It currently installs the toolchain into the root of the system drive, which is controversial and dangerous. We have no idea if there will be sufficient space. It is not without precedent, though. The tree structure within the toolchain does have a more traditional Unix layout. Finally, to round off the weirdness of the system, the installation also draws inspiration from Mac OS and merges that into the layout. This provides a very flexible system, even though it is unfamiliar to Windows users. Like Visual Studio, the Swift toolchain is set up for multiple parallel installations of the toolset. Similarly, the layout is set up for multiple parallel SDK installations so that cross-compilation is possible and simple. The layout compactly encodes various bits of information. Each toolchain is identified by a tuple of vendor, variant, and version. The vendor identifies the distributor. As there is no commercial entity for this toolchain, unknown is used as a placeholder. The variant allows for parallel variants of the same toolchain, such as asserts or no asserts. Each platform is installed into its own root. Contained within are multiple versions of the SDK and developer tools to augment target content, such as the testing framework. In order to compose the paths, environment variables are configured, namely developer dir, which gives us the base of the root paths, and SDK root, which is meant to be the root of the current SDK in use. For tooling, property lists augment the environment variable for platform or SDK level information. The LLVM manifest tool, unfortunately, is not sufficient for all of Swift's need. In particular, it cannot yet embed executable manifests into binaries. This requires users to sometimes fall back to MSVC tools for certain actions. There are areas where LLVM still has room for improvements when it comes to packaging toolchain distributions. A toolchain distribution often comes with runtime libraries. In 2016, Chris Bieneman introduced the Runtimes build. For Swift, this allows handling the profiling runtime. The system still does not scale for Windows, where you cannot necessarily cross-compile without environment changes. Some runtimes have external dependencies, such as ICU and SQLite. The system assumes a CMake-based build, which is not a universal given. Existing libraries such as SQLite and ICU do not have a CMake-based build. Modern languages are more complex, often having custom package management systems. This does not integrate well into the LLVM system, which is designed for C and C++. The build system does not make cross-compiling entirely easy. With tools like TableGen needing to be built for the build host and the need for building with MSVC, the build system often requires manual orchestration and strategic changes to enable the builds. The process of packaging the toolchain led to some interesting lessons. The first one was to prefer MSVC over LLVM wherever possible. This led to a nearly 5% build time reduction. Although in the case of Swift, this is not always possible. There are portions of the build, such as the Swift runtime, which absolutely require Clang to build. Another finding was that using the LLVM enable tools to add an out-of-tree compiler is very helpful, yielding another 5% time decrease by enabling better job scheduling for the build. The last thing that ended up working out rather well was having multiple caches and composing them together. This simplified sharing flags across the various components which are built outside of the LLVM projects and Runtimes builds. Finally, explicitly configuring all the options to minimize the build targets can save a lot of time. If you're interested in hearing about some of the challenges to the port, I suggest you check out my 2019 LLVM dev meeting talk linked here. Swift on Windows is now just a win-get away, so do check it out. Thank you for your attention, and I hope you enjoy the rest of the conference.
Great. Thank you so much, Salim. More interesting challenges for sure. Okay, next up, we're going to have Alex tell us a little bit more about Clang vendor options. And Alex is a LLVM contributor from Apple. Take it away, Alex.
Thank you. Hi, everyone. I'm Alex Lawrence, and let me share my presentation.
Alex, are you able to mute your speakers?
Can you not hear me?
Just getting feedback.
Oh, sorry about that. Let me try my headphones. That might be better. Hello, can you hear me now? Is this better?
Yeah, sounds good.
Perfect, okay. So let me start by playing my keynote. Perfect, okay, so as I mentioned, my name is Alex Lawrence, and I work at Apple, and I primarily do a lot of qualification and integration work for the new Clang releases. So at Apple, we have a downstream toolchain which ships Apple Clang, and that toolchain is used to build our operating systems like iOS. And a public version of this toolchain is then also used by the app developers who use Xcode to build apps for the App Store. And so whenever we want to create a new release of Clang that we would like to adopt for our internal software, we have to go through an extensive qualification process because we are not allowed to break any Apple software whenever we adopt the new compiler, as it would cause a lot of disruptions to all of the other engineers in the company because they typically live on the latest builds that are released every day. And additionally, we also can't mix and match different compiler versions when we're building Apple software. So we must get the release right at the very first time, as it needs to build everything without any regressions. So in the past, we only used to do a couple of releases a year, and they were basically qualified as needed. But our long-term goal is to do more frequent releases so we can adopt new Clang and LLVM changes sooner rather than later. And so in line with the goal, over the past year, we started testing our downstream main branch by building and testing our operating systems on a weekly and even sometimes daily basis, as our goal is to deploy the latest compiler more frequently. However, since Clang and LLVM are actively developed projects, they get a lot of changes every week. And this is great because they get a lot of fixes and improvements, but it also complicates testing and adoption for us, as some changes cause issues in our internal software, like new compile errors in projects that we're building, and also different runtime regressions like test failures, crashes, and other unexpected behavior. For example, some UI elements on an iPhone might be incorrectly positioned after the new iOS is built with the new compiler. And so all these issues that they can negatively impact our ability to test the compiler on a continuous basis, because issues tend to accumulate and they tend to hide other issues as well. So we're not really getting great test coverage after a while. And also this complicates the release process for us, because whenever we actually want to create a new release, we don't really know how well the compiler is tested. So we have to do additional work to qualify it separately outside of our downstream main branch. And so we came up with a solution for how we can manage new changes that cause issues for us. And so the idea that we have is that we should try to manage them by either disabling them or by tweaking them as needed to remove the effect that causes the issue. And so obviously some compiler changes have compiler flags that can be used to disable or to tweak them, but not every change has that. And so whenever there is an appropriate compiler flag we can use, we can obviously adopt this and use that whenever we're building projects. But for other changes, we need to add new compiler options or flags as well. And so to help with this process, we have developed a support harness in Clang that can be used to add custom downstream compiler options and flags with as minimal downstream diff as possible, and that can be enabled based on the vendor's individual requirements. So at first, I'd like to talk about the vendor options support that we have added to the harness. Essentially, they're Clang language options that are declaratively declared downstream, and they can be controlled. So you can control when the driver wants to enable them. And they come with a generic Clang flag, which basically specifies the name of the option to enable or to disable. And they do require some downstream changes in the compiler to actually, take advantage of the option and to use the option. But a lot of the time, those changes that are needed are quite minimal. So this is an example of a vendor option that we declare downstream. So it's declared in like this macro syntax in a .def file. It has a name, and then similarly to Clang language options, it has basically the amount of bits it needs, the default value, the description, and then we have a predicate as well that can be used by the driver to know when to enable it. So in our case, we wanted to enable it for all of the Darwin OSs. And an example of the change to the code that's actually needed to actually use this option is shown below. So basically, after creating this option, we only need very minimal downstream diff to actually use this option. And all of the other things that are needed to support a Clang language option, like serialization, like driver or compiler instance support, are already handled. So you don't really need to do anything extra, just add the option and then add necessary code to actually use this option, and that's all you need. So yeah, as I mentioned, typically you only need minimal downstream changes, but this really depends on the change that you're trying to control. Sometimes you do need some more changes than just the one line diff I have here, but most of the time it's pretty simple. And in addition to vendor options, we have also support for different compiler and LVM flags as well in our harness. So similarly to how we control when the driver enables vendor options, we can also control when the driver wants to specify and add the different flags as well. And most of the time we use existing flags, but sometimes we need to add new flags as well if they're not yet implemented. And this is an example of how we can use an existing LVM flag and to enable it for, in this case, we're actually enabling it for a specific project, but this code isn't shown here because it's kind of like very specific to how Apple handles projects. So it wouldn't really be useful to demonstrate it here, but you can see that we're passing in the actual flag and the value we want to set, and also like the description, and it also has a predicate as well. In addition to controlling new changes through options and flags, we also need to control new diagnostics that Clang adds, because we build a lot of code with W error, and sometimes even W error, W everything. So as you can imagine, this can cause a lot of build regressions that just pop up in different projects whenever Clang adds new diagnostics or tweaks existing diagnostics. So we sometimes need to disable new warnings that cause a lot of build failures in different projects. But the good thing is that our users can still pass W, the flag to enable the diagnostic explicitly if they want to use it once the new compiler release is created. And sometimes we also have to disable W error promotion for specific diagnostics, for specific projects, just to get them built in again. And we have to wait until the individual projects at Apple fix their code to actually re-enable these diagnostics for them. And so this is our mechanism for how we do that. So we either here have an example where we disable a new diagnostic outright. And again, we have a little comment here saying like why this is needed, and we list specific Apple internal issues there typically. And also, and the second example I have here demonstrates how we can use the same mechanism or a similar mechanism to essentially disable error promotion for a specific project like WebKit in our OS until they resolve their build issue. So yeah, these are all of the things we use in our harness to actually help us to control the new Clang changes that come in. And so the benefits that I've seen so far is that we are able to continuously test our downstream main branch without being blocked by as many unresolved project issues as we have in the past. And as well as that, the nice thing about this harness that allows us to add the downstream options and flags is that there's typically minimal downstream diff that's required for each change. So we are not blowing up our diff, and that makes it easier for us to maintain and keep merging the upstream changes as well. In addition to that, also because we can granularly specify whenever we want to control each option, a flag, or even a diagnostic, we don't need to turn them off entirely. We can turn them off for a specific project or a specific file even sometimes. And that allows other projects or other parts of the OS to start using the new compiler change and start living in it and start basically taking advantage of it sooner than later. Also, the nice thing about this declarative style which we have is that we can generate reports automatically to see where we're at in terms of like how many issues are outstanding and how many project changes are still needed to actually re-enable a specific compiler change. So this is another handy feature to have. So right now, all of this harness and vendor options that we have are internal to our Apple Clang compiler, but we would like to upstream the harness so it's easy to add custom vendor options and flags upstream as well. So we could potentially move some of our own options and flags upstream to the upstream Clang, or other vendors could use the same machinery to add their own options and flag downstream or upstream. So reach out to me if you're interested in having that upstream. For now, I don't have a specific timeline when we would actually upstream this, but if there's interest, I think we can try to do it sooner rather than later. Yeah, so in conclusion, the vendor options and flags that we have in Apple Clang help us control new compiler changes that come in from upstream. The downstream code diff that we have is minimized because of how the harness deals with a lot of boilerplate code that typically would be needed otherwise. And we can continuously test our software without being blocked on as many project issues and other runtime regressions as well. And because of that, our downstream main tracking branch is better tested and better qualified. So we're getting a lot more test coverage on all of Apple software whenever we are testing new main branch commits. And this also helps us with creating new Clang releases, or Apple Clang releases in this case, because whenever we want to create a new release branch from our downstream main branch, we already know that the main branch is in a specific state and certain issues are present and certain issues have been fixed. So it's now easier for us to actually go through the release process and to finish the qualification and then actually enable the new release and enable it across all of Apple software because of that. So yeah, that's all I had for today. Thank you for listening, and I hope you enjoy the rest of the conference. And if you have any questions, feel free to either send me an email or add them to the GitHub issue for this talk on the GitHub repository for this conference. Yep, thank you.
Great. Thank you so much, Alex. It's really cool to see a peek into how you all work on addressing some of these issues. In particular, we already have some folks on the Android side chuckling in our team chat saying, yep, we've seen the similar kind of issues before, kind of thing. So definitely, interesting to see similar problems on all over the place, kind of thing. So just for some logistics for the rest of the conference, we have a 15-minute break scheduled. It's perfectly okay if speakers need to cut into that break time a little bit. That's meant to be kind of overflow. I made a mistake configuring the stream, so the live chat wasn't enabled from the get-go. So sorry to our earlier speakers, but the live chat should be enabled now. It looks like it is on the YouTube stream. Folks may need to refresh if they have the stream open to get the new UI update to have the live stream. Otherwise, if folks want to be posting questions, I'm pretty actively monitoring multiple channels in LLVM's Discord, multiple LLVM-related IRC channels, our GitHub issue tracker, and of course the live stream, and finally our internal chat as well. So if you're trying to get a hold of one of the speakers not through any one of those channels, you might want to try one of those instead. Otherwise, we'll be back again at 9:25 in less than 15 minutes now, where we'll hear from Carlo about the use of LLVM and distributing LLVM through Homebrew package manager. So thanks again for attending, and we'll see you in a little bit. Okay, and welcome back from the break, everyone. Next up, we're going to have Carlo is going to be telling us a little bit more about packaging LLVM for the Homebrew Package Manager. And Carlo is joining us today from the Philippines. Welcome, Carlo. Take it away.
All right, hang on. Let me hide my presentation. All right, there we go. Okay, great. Thanks for having me. I'm here to talk about Homebrew's distribution of LLVM. And let me give you some background about Homebrew first. So we are a rolling release package manager for macOS and Linux. Homebrew started life as a macOS only package manager, and then someone forked it for use in Linux, primarily for use in HPC systems, and now we work in Linux too. We ship binary packages for Linux machines running on Intel and the latest 3 versions of macOS. And I think 2 things are primarily determinative of our approach to package management. The first are resource constraints, and second is the profile of our average user. For resource constraints, we rely very heavily on macOS CI, and that's not as easy to come by for an open source project as it is, Linux CI. And second is as you can see, we have 25 maintainers maintaining 6,000 software packages, so we're a relatively small team. The second thing, the profile of our users, we are still primarily a macOS package manager. That means most of our users are running macOS. And I think something that is true about macOS users, even ones who develop software in their machines, is that we prioritize simplicity over, say, customization. And this factor, and indeed resource constraints that I mentioned earlier, drives a lot of the design and packaging decisions we make at Homebrew. And you'll see this reflected in the way we package LLVM as well. We host everything on GitHub, and this is useful for 2 reasons. First, it makes automation really easy. Second is that it makes barriers to contribution from the community when it comes to maintenance of both Homebrew itself and the packages we maintain really low. And we rely on both of these things very heavily to keep things running. Okay, so that's it about Homebrew. Let me tell you about how we package LLVM. So we want the package that is simple to use for our users, simple to understand for our users, but also simple for us to maintain. And that leads us to bundling everything, all of LLVM and the various sub-projects that we build as a single package, which you can install with just brew install LLVM. I think that we have a reasonably complete LLVM distribution. You can see this in the next bullet points, the next 2 bullet points. We also make heavy use of the Runtimes build, which we heard about earlier. And I think that the Runtimes build, so Peter told us about the benefits of using Runtimes build. I think there are 2 more, at least, that's useful for us in Homebrew. The first is that it helps us bootstrap with just GCC 5 while carrying only a small patch for LLDB. I think that our build would require much more extensive patching if we wanted to continue bootstrapping with GCC 5 if we didn't use a Runtimes build. So that's the first reason why a Runtimes build is useful for us. The second reason why a Runtimes build is useful for us is that when we build, so we build with PGO and macOS, and using a Runtimes build enables us to limit the build times of our stage 1 compiler, because now we don't have to build so much into it. For example, we only configure our stage 1 build for a compiler for the native target, and if you didn't use a Runtimes build on ARM macOS, say, you'd have trouble building OpenMP. All the gory details are in a link in the last bullet point. My slides are going to be available in the conference repo later on. So this is just a link to our build configuration for anyone who's interested in looking at it. Okay, so that's how we configure LLVM. How do we test our distribution? So as I've mentioned, everything happens on GitHub. So any changes made to the LLVM formula, which is Homebrew parlance for our package specification. So any changes made to that is made via pull request. Pull request triggers CI, and what CI does is a full build, and it runs a series of smoke tests. And what these smoke tests look like, I would have talked about them a bit more, but it turns out that they look a lot like what you're going to see, what you see in the LLVM Toolchain integration test suite, which I believe we're going to see a talk about later today. So aside from doing a full build and running some smoke tests, what our testing system also does is that it takes the dependency graph of our package repository, picks out all of the packages that depend recursively on LLVM, and also runs a bunch of smoke tests for these packages as well. Okay, so I've told you how we configure, how we test LLVM. What are some things we could do better? Or the first thing that I think that we could do better is that sometimes some users just want Clang tidy. And if you're a user that just wants Clang tidy and you're using Homebrew, it's not great to have to brew install LLVM because you're getting all the pieces that you're not really interested in. The second thing I think we could do better is to cache our bootstrap more extensively. Because, so as I've said, we do a 4-stage PGO build on macOS, and that takes about 2 hours on ARM macOS and about 16 hours on Intel. And that's not great because when someone opens a pull request, typically the only changes they're going to want to make are for the 4th stage of the build, the bits of LLVM that we're actually going to install into a user system. So that means the first 3 stages are essentially, nothing changes here, which means that, if we could just bootstrap it, then, if we could cache those stages, then these CI runs and these pull requests will take much less time. The next 2 bullet points are related. I think that, I've told you a bit about how we test it, but when I describe our testing framework as, a bunch of smoke tests, that's not an exaggeration. I think that it would be nice if we had more comprehensive test coverage for our builds, but also I think that it would be nice if we could test release candidates a bit more proactively, which is something that we're not really able to do so often. And that's going to be helpful for a point that I'm going to mention a little bit later. The last thing that I hope to be able to do soon is to, if I could find some time for it, is to enable LTO builds in macOS, which is something we don't do currently. So the current barrier to it is that there's a question of portability, because our distribution does include static archives. But the reason why I think it's going to be possible is that we kind of do the opposite of cross-compilation when we do our builds. That is to say, whatever we install in a specific macOS version, we also build on that same macOS version. So if you install LLVM in Big Sur, that means that binary package of LLVM you've installed was also built in a Big Sur machine. And I think this is going to alleviate some of the concerns about portability. But again, investigating this takes time, yeah, I just hope to invest some of it soon. Okay, so those are things we could do better. What about things we struggle with? The first thing I think we struggle with a lot is that there's no ABI versioning for liblllvm in macOS, and that's not great because that means that whenever we update our LLVM package, we're never really quite fully sure if things that link to it are still working. And the second thing that actually makes this quite problematic is that it means that LLVM config is very subtly slightly broken on macOS, so it doesn't quite work the same way you would expect it to as it would in Linux. So at least not without a post-install workaround, which you do carry around in the LLVM formula. The second thing that we struggle with a lot, well, I don't know about a lot, but we do struggle with a bit, is that we also experience build failures and tagged releases of LLVM. This happens even in point releases, which is a bit surprising and a bit frustrating. And that's kind of related to the point I said earlier about maybe we'd run into this a bit less often if we were a bit more proactive about testing release candidates. But there you go. Okay, so actually, I think that's pretty much. So I've got a bit of time left, but this is really all I prepared for today. If you've got questions, comments, or contributions, please ask questions at the issue that I posted on the conference repo. If you have any questions for Homebrew, we have a discussions page on GitHub. Please feel free to post any questions there. But the last thing that I think I want to emphasize is that if you've used our distribution of LLVM and it's not quite working for you, or if there are things that could improve, if it could improve our distribution, please do open a pull request. Some recent significant improvements to our LLVM package were actually made by an LLVM developer at Google currently. So if you're listening to this, we'd love it, and how to make our distribution better. Our small team and our many users would love it if you could do that. So the last slide, I do actually have one more slide, but I'm not prepared to talk about it now because it's going to take quite a bit of time. But I put it here anyway because I'm going to post these slides eventually. Is that I do think that there are some gotchas that we've encountered about building LLVM. And in fact, I think Peter might be interested about using runtime. The first point here about using a runtimes build. But yeah, so it's going to take quite a bit more time to talk about these. So I've just saved this last slide. You can check out if you're interested. And these are issues we face that had workarounds that I don't think have been documented anywhere. So I think that putting this out there, I think, might be useful. So, all right. That is it for me.
Great. Thank you so much, Carlo. It's a fantastic piece of software. Really, I always enjoy the use of Homebrew. So thank you so much for your talk today. And if folks have feedback, make sure to check out the GitHub issue tracker. Barrow, are you ready to go?
Yeah, sure. For some reason, my camera isn't turning on anymore, but I'll be presenting slides anyway, so...
Sure. You want to give it a shot?
Sure.
Cool. Looks good. Take it away, Barrow.
Okay. So this will be about switching a Yocto-based distribution to LLVM. So we started developing a new operating system that's currently being referred to as All Scenarios OS. And it will be a little bit further down the road a new portable OS for anything from small IoT sensors to rich multimedia companions. And as such, the OS environment can sit on top of multiple different kernels. So higher-end devices will use Linux, while some of the lower-end devices will be running Zephyr, FreeRTOS, or Huawei's own LightOS. And on top, there will be a little layer that presents the same APIs on top of every kernel, so that applications developed on one will definitely run on the others. One of the ideas behind it is reusing as many open source components and sticking with open standards as far as possible. And we decided not to reinvent the wheel in this, just start with something that's already good at building minimalistic OSs, which is Yocto. To make sure that we can supply security fixes for a long time, the decision was made to base the work on the long-term support branch of Yocto, which is Dunfer. But there's a problem with that. Going with Dunfer means having GCC 9.3 as the main compiler. And we don't want to become a museum of outdated components. And we need RISC-V support. We want Cortex-M optimizations. So sticking with the GCC 9.3 toolchain was not an option. So there are two viable options that could get us to from Dunfer to where we want to be. One would be updating GCC to 11.2, and the other would be switching to Clang. Actually, we ended up doing both. We made the decision to switch to Clang, in particular Clang 12. We might move to 13 at some point before the first release, but the first release is scheduled really soon, so chances are we'll be staying on 12.01. And GCC 11.2 is available for builds that need GCC for anything. But we have decided to go with Clang 12 as the main compiler for everything. And given we don't have to care about binary compatibility with older distributions, unlike the other project I'm going to talk about in another talk in this conference, we've decided we can go all the way. So compiler RT is in, libc++ is in, of course, only on devices that actually need C++. Some don't. And the default libc is muzzle122, so there's no need to build glibc for most use cases, because glibc still would require using GCC for the libc build. So the decision was to go with LLVM components wherever it's possible. So how do you do that? Fortunately, there already is a Clang layer for Yocto. It's not an official component that comes in when you download the Yocto build system, but it works pretty well. It's actively maintained. There's a link to where it is in the slides. You pull that in like you would pull in any Yocto layer, and then you edit your local configuration, set toolchain equals Clang, and you're ready to get started. Unfortunately, if you're on the long-term support version, it's not quite that funny, because then you'll get LLVM in Clang version 10, because the long-term support version was branched off. So instead of using the long-term support version of MetaClang as well, we decided to pull in the master branch of MetaClang and bring back support for the long-term stable release of Yocto in the master branch. Our working tree is linked in the slides in case anyone is in a similar situation and wants to use Clang 12 on top of Dunfer. It's also being upstreamed. There's now a Clang 12 branch in MetaClang that is based on our work. But at the moment, our branch is still a little bit ahead. So chances are you want to check out our branch if you're in the same situation. MetaClang, and of course, forks of it allow a way to deal with packages like glibc that need a GCC-based toolchain. There's a configuration file in which you can mark specific packages that need to be built with GCC, even if the main toolchain for a system is set to Clang. So that helps with stuff like glibc for builds that need it. Outside of being a useful workaround for people who want to use Clang but don't have the time to fix every package that doesn't build with it, I think that's an interesting place to look if you're a Clang developer who wants to know where there are any pain points where packages still need GCC. So I've linked the Git repository that has this file, and you can just go to the presentation, follow the link, and you will get a list of packages that still need workarounds, that still need to be built with GCC, or that need specific compiler flags like -f no integrated AS. But we'll get to that again in a bit. So looking at this thing, we figured out that some workarounds tend to stay a lot longer than they are actually needed. If you look at the non-clangable conf file that I've talked about on the previous slide, you will see that it works well, but some of the workarounds are forgotten about and just kept forever, even when they are not necessary anymore. That certainly goes for setting a toolchain for whatever package to GCC. You forget about it, that package just keeps building with GCC forever and forever. even after you've updated Clang to actually fix the bug that was causing it, or even if you've updated the package to make it compatible with Clang, people just don't check again and just leave the workarounds in there forever. So we've had a look after rebasing everything. We found 7 instances of settings where packages were just built with GCC for no apparent reason, so we could remove that. 5 instances where people added -f no integrated AS, even though that is not needed anymore. 1 instance of -f no integrated AS being set globally for a package when it was actually only needed on ARM32 because of the buggy ASM constructs. One of the more interesting things is we could fix a couple of packages that still use GCC with minor patches, but one of them was really interesting because the thing causing the breakage with Clang was actually quite a big bug that just went unnoticed forever. If you look at the removed line, you'll notice there's a comma missing between void and _bool. So what GCC does is it concatenates those strings and looks for void _bool, which of course it will never find in real code. Whereas what was meant was looking for void and for _bool. Clang issued a warning since the stuff was compiled with the -w error, issued a compiler error, but the usual thing applies. People thought, oh crap, that shitty other compiler doesn't compile my code. I'll just switch back to GCC and edit that workaround toolchain equals GCC for the package in question instead of fixing the real bug. So supporting different compilers is a good thing because different compilers point out different valid bugs. So things to take away from this: certainly look at what your compiler is telling you instead of complaining that the compiler is buggy and running back to what you were using before. The compiler might just be right. And that applies to both switching to a different compiler altogether and new versions of a compiler. Just because there's a new error in your code doesn't mean that Clang 13 or Clang 14 is broken or that GCC 12 is crap. Look at what the compiler is actually saying instead of blaming it. The second thing, revisit workarounds from time to time. They tend to stay around forever because they don't break things and they were needed at some point. But if you forget about them, they will stay there even when they are no longer needed, and they will just be propagated forever, causing all sorts of problems. And lastly, non-clangable conf, which is the file that lists packages that must be built with GCC or that require special compiler flags, is an interesting thing to look at, even if you're not using all scenarios or Yocto or anything. So take a look at that file and try to help us fix the code that still needs GCC. Yeah, that's all I have for this session. Thank you for your attention, and if you want to get in touch with us, the contact channels for the Open Source Technology Center are right there.
Great. Thank you so much for your talk, Barrow. It's very interesting to see everything that's going on in the world of Yocto, and get a kind of a status update really on this status of building so much software with Clang for sure. We'll be hearing from Barrow again a little bit later. Barrow, maybe you can give it a shot trying to reload your webcam kind of thing, because Barrow's got some awesome dogs who might make a guest appearance in the later talk kind of thing. Peter Smith, are you online? You think you're ready to go, even if we're running a little early?
Yeah, I can be. I've just got to work out how to drive this thing. So I think if I do, okay, present now. Okay, can you see that?
Looks great.
Okay, right. Okay, so are you ready to go?
Yeah, it's all yours. Take it away.
Okay, right. Okay, so I'm here today to talk about the LLVM embedded toolchain from ARM. Hopefully I got all of those words in the right order. So just to start, I just wanted to go through and sort of, mention what is an embedded toolchain, because quite a lot of people will be very used to, I guess, a desktop sort of focused toolchain, but not necessarily an embedded toolchain. So embedded toolchain is basically something that targets embedded systems, sometimes called bare metal systems. So you'll notice in Clang there's a bare metal driver for these types of systems. And essentially a bare metal system gives you no assumption of an underlying operating system. So for example, your platform can't assume that there's an operating system to do synchronization, create tasks, create memory, that type of thing. Typically, you'll end up targeting a very small embedded device, although that's not necessarily always true. So almost by definition, you're doing some form of cross-compilation, even if you're cross-compiling for the same architecture. In theory, you can run Clang on an ARM system targeting an ARM Cortex-M device, but you're not going to run a compiler on a Cortex-M device, certainly not one with 4K of memory or something like that. You're almost always doing static linking. Quite often, you're not actually running the ELF file that's produced by the linker. You might even be extracting that and burning it to flash, that type of thing. These embedded devices have got weird memory configurations, so you're often looking at a complicated linker script to sort of place code at various points in flash. You've then got startup code that might copy some of that to faster memory, that type of thing. Because a lot of these devices are quite diverse. They often support lots of different features. Some of them have got floating points, some of them haven't, that type of thing. So you end up with lots and lots of different library configurations. Typically, as well as I mentioned, some of these devices have very little memory. So we want to optimize for code size often rather than performance. And of course, compiling your code and downloading it to these awkward little devices is a pain in the neck. So quite a lot of the time, you'll actually debug your code on an emulator, often using something called semi-hosting. And semi-hosting is kind of a way to do some actions on the host. So that would be something like open a file. So your embedded device might not have a file system, but your desktop machine that's with a debugger does. So you can do all sorts of testing or compiler testing by using semi-hosting, which effectively sort of instructs the debugger to do something on the host machine rather than running on the target. Of course, you don't ship the end program with semi-hosting support. It's really a debugging tool. Okay, so moving on to the LLVM embedded toolchain for ARM. So the LLVM embedded toolchain for ARM is very closely modeled on the GNU ARM embedded toolchains, which some of you who've done any embedded development on ARM may be familiar with. So this is basically I'm talking about the GNU ARM embedded toolchain here. It's essentially I guess, starter kit as such that bundles the compiler, bin utils, debugger, and a C library and some example projects that sort of enable you to get started. So this is sort of, I've just got a Cortex-M development board or something. I want to do some development on it. I can download this embedded toolchain and I can download something and have a fighting chance of getting it working. I say a fighting chance because it's not simple even when you download this. It's not a fully featured, I guess what you would call a SDK for embedded chips like you might get from a vendor. But anyhow, this is effectively the LLVM equivalent of that. So what sort of things would it come with? It comes with the compiler, the LLVM bin utils like LLD, that type of thing, LLVM objdump, compiler RT for the runtime library, C++ libraries from LLVM. We don't yet have a C library that's really suitable for embedded development. So we've packaged newlib in the same way that the GNU ARM embedded toolchain does. But anyway, also provide some sample linker scripts, some example projects that can run on an emulator. We've tried to use as much as possible from the LLVM project, newlib probably being the exception. We want it all to be open source components, buildable by open source tools. Our end goal is for a binary release. We're expecting there to be sort of two types of user for this. The first one is basically someone who's just got a development board, wants to download a toolchain and get going quickly. The second type is for, say, what I'm going to call it, well, we call them SoC vendors, system on chip vendors. This is somebody who's actually built one of these development boards and they want to bundle a development environment for it. So something like this toolchain is something that could be suitable to be bundled behind, you know, an IDE. I think Eclipse is a popular choice for a lot of these sort of things, but that would then get bundled up with other libraries and device drivers, that type of thing. Okay. So the project structure at the moment is essentially a set of build scripts. So obviously, we're taking LLVM and NewLib open source repositories. So effectively, what we're doing is extracting known revisions of those open source projects, building them, combining them with linker scripts, running them against some tests, providing some source code samples and some documentation. So it's all fairly small and simple at the moment. But the main idea is to do as much work as possible within the open source projects themselves. Okay, so this is an example of how you might use the embedded toolchain. So certainly if you just use the GNU embedded toolchain today, you can't just say, you know, compile something with and just with no extra command line options. There's often some extra things that you would have to put on there. So quite often the GCC toolchain will use something called a specs file. So you'll notice in that example there's nano.specs and rdimon.specs. So nano is basically saying use newlib nano rather than newlib. Newlib nano is the small version of newlib. rdimon is essentially the code name for semi-hosting. So obviously you wouldn't use that for a shippable product, but you would use that for testing. Now, as I mentioned before, you've got complex memory map in all of these devices, so you can't rely on GNU LD's built-in linker script. You have to use your own one there. And yeah, that would be a sort of typical invocation that you might work for a toolchain. Okay. So another thing that you would also come through for here is multi-lib support. So Peter mentioned these earlier on today, I think in the context of the runtimes. So we do have for Clang the ability to sort of choose the variant of compiler RT dependent on what architecture you pick. As far as I'm aware, we don't have that ability in the bare metal driver for actually picking the C library like GCC does. So if you notice there, if we print the multi-libs, you'll see that there's various different ones, like there's an ARM one, there's a Thumb one, there's one for V7, which will map to, say, a Cortex M3 or something like that, and the V6M, which is a Cortex M0, that type of thing. And you've got the various floating point variants, like no FP for no floating point, which would be software floating point, soft FP, which is a kind of hybrid between, which uses this. You basically pass the floating point on registers, but on basic core registers, but you don't. You can still use the floating point unit for computation, and hard is you pass floating point registers or parameters in floating point registers, that type of thing. But you can see there's quite a lot of variants for these. Okay, so specs files. This is just basically a printout of one of the specs files, so you can get an idea of what some of these are doing. So essentially, if you can see there, it's essentially saying, okay, this is for the semi-hosting spec, which is rdimon.specs. It's saying if the nano specs file is not present, then we just want to link the C library -lc. If the specs file is present, we want to change the command that particular link flag to lc_nano. So it's giving you a little bit of configuration or runtime choice. It's all fairly simple substitution-based stuff, but it does give GCC quite a little bit of flexibility to sort of build up some of these commands that sort of make it a little bit easier to do embedded development, where you've just got so many different choices in what you actually need to set up. Okay, so how do we approach some of these things with LLVM. So one of the first things we wrote up, there's no bare metal multi-lib support for C libraries. So for example, when I mean C libraries, this is the new lib variants that we've built. So as I said, we do have support for runtimes in compiler RT, but not for new lib as far as I'm aware. So what we've done here is we've basically used the Clang config files to sort of basically approximate this. Now, Clang config files are not as flexible as GCC specs files. So essentially, we've had to basically duplicate these for all of the various bits. So we've got a profusion of config files. And we've also made a very small downstream modification for these with this $@, which basically sort of means current path, which has made it a little bit easier for us to sort of specify where the library directories are. So what we really want is multi-lib support in the Clang driver. So this would be when you just say target v8m-none ABI, or giving the architecture v8m plus .main plus fp. That would be enough for the driver to figure out, I need to select this particular directory to link the C library out of, and it would need some intelligence in the driver to be able to do that. Okay, some further challenges. When we tried to compile newlib with Clang, we found that there were a few problems. So some assembly is accepted by the GNU assembler, but not by Clang. These are all fairly trivial things to fix. This is basically just, I think, the LLVM integrated assembler doesn't support some of the sort of abbreviated forms that GNU assembler supports. Certainly, I'm going to shout out to the Clang built Linux project here for vastly improving the Clang integrated assembler. So this would not be possible at all without all of that work. There's also an attribute naked function that is incompatible with Clang, but luckily that's in the Linux part of newlib nano, so we just remove the attribute naked because we don't really care about that particular function. It's never actually selected at link time. We also found that newlib didn't have some of the aligned allocation functions that meant that we can't use C++17 aligned allocation with that. Yeah, and also one of the things that you almost always come across when you're doing embedded development is what's the trade-off between code size and functionality. For example, if you're building, say, and for an embedded system that doesn't have any input and output, using IOStream with full locale support is normally a huge amount of code size. Exceptions in RTTI are also something that you don't really want in a lot of cases, but you've really, unless you sort of keep multiplying the number of library variants you're selecting, you pretty much have to pick a few of them. Now, one of the main goals of the project was to be able to support Windows, because a lot of embedded developers, particularly sort of, I guess, ones just starting out, want to use Windows. So we're using Min-GW GCC for the moment. So that adds some dependencies on some Min-GW DLLs, which we want to remove. So we're currently sort of looking at how do we support Clang CL or MSVC, that type of thing. We're testing internally at the moment using ARM fast models because they support all of the platforms that we're targeting. QEMU can be used if it has a system model that fits your purpose. So, for example, QEMU supports M0, M33. I'm not entirely sure whether it supports the very latest stuff that's just come out. Okay. So where are we now? Where do we want to go? Effectively, at the moment, we're source only, LLVM 12, x86 Linux and Windows, and our C++ support is missing exceptions, RTTI, IO streams, TLS. Testing, we're testing the build scripts, but not necessarily the tools itself, and we're doing some benchmarks internally. And effectively, I say I'm running out of time, so I'll probably best skip the plan stage. But effectively, we just want to keep adding support and add CI.
Take your time, Peter. We can go into the break if we need to.
Okay, sure. So so the thing that I guess we say what we'd like to work with the community here is that we'd like to get some better multi-lib support in the bare metal toolchains. I'm thinking in particular here for things like the C library. Now, GCC does this at build time with a config file. As far as I'm aware, at least some of the existing multi-lib support, I could be wrong and this could have changed since I last looked, is that the Clang multi-lib support does kind of rely on you to hard code some paths from time to time. So whether these, I'm just thinking here, is there a way of solving this problem in a bit of a better way? You know, is there even a scope for being able to give a config file that tells Clang what the multi-lib support is, so it can kind of work things out? Because I mean, these things can be solved. So, for example, each tool chain might be able to say, oh, it's just a simple downstream patch to put my directory structure in. But it would be nice to have that supported outside of that. So some potential for expanding config files to support some specs-like features. Now, I can remember going back to the original discussions about config files, and specs did come up at that point, and there was always a sort of, do you really need to support that level of complexity? So I'd say the jury is out as to whether you really need that for everything. It may be that once you've done all the multi-lib, the amount that you need to do in a specs file just drops away, and you can get away with it with just standard config files. Perhaps the most important thing that we'd like to do is build bots, and more continuous integration. So at the moment, ARM and AART64 are well tested for Cortex-A. Linaro provides some build bots for that. But currently, we don't have any upstream coverage for things like building, say, compiler RT for all of the different Cortex-M devices, that type of thing. So that's something that could be done and could feed back to the community, that type of thing. We're also thinking about, well, the LLVM test suite is not ideal for small embedded systems. There are quite a lot of heavy programs that probably aren't really going to work very well for testing. But one of the things that we could do is perhaps, internal testing on other things, or maybe other embedded sort of systems, and use something similar to Linaro's Clang Linux kernel bisection job. So basically, when there's a build failure, it can bisect to work out, which change there, give the person who broke that particular program a reproducer, that type of thing. Say something like a Docker container they can download, that type of thing. Anyway, I'm definitely going over time now, so I bet I'll just pass through these really, really quickly. So yeah, if you've got any questions on the talk, that's the please put those in the Distributors Conf. There's a link to the repository there. So if you want any kind of feedback on the toolchain itself, want to try it out, just please raise a pull request on or an issue, that type of thing. There is a larger presentation on this given last week by my colleague Mikhail Maltsev at Linaro Connect. So if you want to watch this in more detail, you can go watch that one there. And there's a link to the GNU ARM embedded toolchain there if anyone wants to pick it up. Okay, sorry for going a bit over time, but yeah, I'll stop there.
No, it was great. And thanks so much again, Peter, for joining us. Sorry for I missed a couple introductions. So thank you, Peter, for joining us from ARM, and Barrow from Huawei's Open Source Technology Center prior to that kind of thing. And, I'll definitely have questions around spec files or something that, at least with my work, I'm not super familiar with them, but I have been exposed to them roughly, kind of thing. So, I'll encourage folks to join our banter. It's pretty much just me and Fangrui in the YouTube live chat, but feel free to hop on and post some jokes or something. Okay, next up, Thomas is going to be joining us from Graphcore and is going to tell us a little bit more about a tool chain targeting Graphcore's IPU. Okay, Thomas.
Hey, can you see my slides?
Yeah, we can hear you. There's a bit of background buzz. I don't know, are you able to switch the microphone to the headset if it's maybe coming from the computer?
I can try, but usually it doesn't work.
Okay, no worries. It's just a little bit of background noise, but it's not a big deal.
All right. Okay. I prefer to keep it that way, just to create any trouble. Hi everyone. So my name is Thomas Prodom, and I'm going to talk about challenges faced by Graphcore when distributed LLVM and some of the solutions we've came up with. But first, a bit of background. So Graphcore has designed a new massively parallel system powered by the IPU chip to accelerate machine intelligence. The IPU chip contains nearly 1,500 cores, which each run 6 program threads in parallel. Each core has its own local fast memory for a combined total of 900 megabytes. Development for this system is made through the Poplar SDK, which uses under the hood LLVM to compile for individual cores and MLIR for some of the high-level optimization. You can find more information on our websites. So our distribution of LLVM is as follows. We take the upstream source codes to which we add all the support for the IPU system. So driver, and backend mostly, as well as our own C library. This makes up our downstream code, which will then build and distribute to two sets of users. The first set is our internal team developing the firmware for the IPU, which will take the source, build it themselves, and then use the resulting binaries Clang to build the firmware for the IPU. For the second set, the customers will build the source and make a Conan package, which will just have all the binaries in it, and will only pick the libraries from the package and include it into the Poplar SDK, which will then provide to the customers. So the customers don't have access to the binaries. They will only receive the libraries, which they will use through the SDK. We'll build for the IPU, of course, but also the host system, which is either x86 or AR64. And we build LLVM, Clang, LLD, all the binutils, LLVM binutils, LDB, MLIR, and some other tools like Lit, FileCheck, etc. So beyond the commits we make downstream to support the IPU, changes to the repository come from two external sources. The first one is merged from the upstream repository, which we try to do as frequently as possible, currently about once a week. And the second is from our fast-changing ISA, and I'll come back to that later. So each of these external changes will come with some issues of their own, which I'm presenting now. So for merges, one of the first issue we have is that quite a number of files, so there's a small list here, will contain target-specific code, but which is inside shared file for all the targets. So one example is the targets.cpp, which has a function allocate targets, which will have a big switch on the architecture. There's not much code here, but what it means is that whenever a new target is added upstream, we'll have a conflict once we pull downstream, because of course we'll add our code for a target, and this will conflict. And if it was just one file, it wouldn't be that big of a problem, but there's plenty, so it's come up quite frequently, and targets get added quite often in LLVM. Another issue is that we want to have as much reviewability as possible. So all the change that we do within the LLVM team at Graphcore should be reviewed, ideally. For merge, it's a bit more difficult, but we've come up with this system where we branch off our downstream branch, and we'll do a merge from a more recent upstream version. We'll resolve the conflict here, and unfortunately, we won't be able we didn't find a way to represent the diff here because there's two heads and didn't come up with a good way. But then there's still quite a lot of changes that needs to be done because API may have changed and we need to adapt our backend accordingly. And what we'll do is that we'll do separate commit for those, individual commit for each separate issue, and in the commit message we'll point to the SHA-1 that introduced that change that require a downstream change. This means that we can easily review those changes, and we have them in the history instead of just one big merge. We have them as individual commits, which makes it easier to look back in time. Once this is ready, then we can merge it into our main downstream branch. Another issue we have is SDAG nodes, so social DAG nodes, which have no natural IR representation. I'll give an example. So any extern, for instance, doesn't have an instruction, an IR instruction that can target it immediately. There is sign extern, so SX and ZX for zero extension, but there's no AX. Any extern node will be created through combined patterns. We could, of course, create a test case that which will end up generating these nodes. But if there is a change upstream that happen to this combined pattern, we could end up having a test case that don't generate any extend and don't test the lowering of any extend node, which is our objective. So we came up with a system to be able to do social DAG unit testing. The way it's working, we've added a couple of intrinsics, one for each shape of SDAG node. So in the case of any extend, it's a unary node which takes one operand and return one result. So we have an intrinsic just for this. And this intrinsic taking parameter the enum value for that opcode, and then as other parameter the operand for the node. So this means it can work with any unary SDAG node. We then have load from an external constant that enum value that we pass to the intrinsic. All these external constants, they are all in the file for all the solution, the SDAG nodes. We have an external constant for each of them, which is in a file that gets substituted here by lit. We link them together, which will make one big IR file, and then call opt with instruction combine to combine these two instructions, so the load and the call, into a single call with a constant value instead of a parameter. Now remains the question on how do we create this file with all the external constants. So this is done through a program that we call ISD opcode constant printer. This program is fairly simple. It just has a long list of mapping from the external constants to the opcode number. So that's the map here we have. It's just a macro, and then the program will just iterate over all so we have a list of mapping. We'll iterate over all the mapping and output for each of the mapping a context expression which assigned to the external constants its value. This will then be compiled by the host compiler, which will the same host compiler with the same flag used to build a Clang. So we'll have all the include path to know the enum value for any given opcode. So we compile it, and then after we run it, which will output the C++, which we then compile with the target compiler towards an IO file. And then, as I said, we link it with the test case, and that's how it works. So this is done as part of the build system inside CMake list, so it's all automated, except for the list of mapping, but we only really need to update it when we want to add a new test case that use a new SDAG node. So it's not really a big problem. It doesn't need to be changed every time that we merge. Yet another issue is the change of behaviors in tools. So one example we had recently was LLVM lit. So we use lit in Graphcore beyond just the LLVM monorepo. We use it in loads of projects, but we don't use it to run the whole test suite. We only ever invoke lit with individual test case. The reason is that we will use CMake as the test suite harness, because we use CMake to build a lot of projects. So lit is still interesting to use for us, because for two reasons. The main one is that it provides this nice pipeline, the run line, which describes how to run the test, and it's part of the test, so it's quite convenient. And the other thing is it provides substitution, which allows us to use the same test case, but compile it maybe for different version of our architecture, for instance. Some of the tests that we have in some of the projects, we want the customers to be able to run them. So the customers will typically use the distribution that they have, like I don't know, Debian or Ubuntu, anything. They'll use their own distributions lit to run the test. Whereas for us, we will use the lit that we build as part of LLVM. That means the test will be run by a mix of different lit version. So what happened recently was that a new behavior, the behavior of lit was changed to error out in case of invoking it on a test case that wouldn't be run if it was invoked on the parent directory. So that's perfectly fine for LLVM test suite, but as I said, for a test case, it doesn't really make sense. We never invoke it in a parent directory. There is a flag to disable this behavior, but any flag in lit, if you try to invoke it on an older version of lit, it will just not work. So since, as I said, we use different version of lit, the customers and us internally, it didn't work. We couldn't either add the flag or remove it. There was always some errors. So what we did is we added a commit upstream to add a lit config option that will allow us to disable this behavior because it's a config option, all lead version will just ignore it, anything they don't understand. Another thing is, and I would suggest people to do that, is to just agree on using leads provided by pip, the pip package, so that we all use the same version. But as a drawback, this means that we cannot have the latest feature. So for leads, it's not really a big problem. We don't use some of the recent feature. But for instance, we still use the file check that we build internally because we want to make use of new features that get added in file check. So we don't have a good solution here. For efficiency reasons, so memory efficiency, that is, I mean, trying to not waste memory and try to get by fragmentation, for instance, we only allow use of static allocation. It also allows us to give us a bit more robustness because we can, at compile time, determine whether we'll have enough memory to run a given program. But that causes a problem because even the freestanding implementation of the current C++ specification requires dynamic allocation. So what we have is downstream we have a very invasive patch that will disable some of the libc++ features, the one which cannot work without dynamic allocation, and which obviously we don't use. And also for other features, we'll adapt it to be able to work with static allocation. But as I said, it's an invasive patch, so it means that if we merge, we'll always end up with loads of conflicts, because the libc++ is actively maintained, which in turn will lead us to maybe not merge as frequently as we'd want. So what we did instead is we copied all the libc++ code into a separate repo, and that's where we do the modification. Because it's a separate repo, we can do that copy and do the changes at its own schedule, and which doesn't slow down the merging schedule for the main monorepo. Note that the current ongoing freestanding proposal no longer requires the dynamic allocation, so hopefully this will no longer be a problem for us. And the last issue we have with merging from upstream is the problem of tests that requires to be run as non-roots. So there's a few tests, so there's like 3 of them here, where they will test an error message when accessing a file with insufficient access rights. And all our CI is based on Docker, where we build and test inside Docker, and we have in our case, all this will be done as roots. We do plan to try to do it as non-root eventually, but it's a bit more complicated than we would like. So for now, it means we run the test as root, and root will always have the sufficient access rights, so we don't have them. So we disable the test locally, but we could instead add a feature in it to just guard these tests based on whether you run them as root or not. If there is interest from other people for that, please let us know, and we'll see through upstream patches to that effect. As I said, another source of external change we have is our ISA. So within Graphcore, to make sure our hardware works well for our software, and we don't build anything useless, but we build something that's that will make the software run more efficiently. We have a software-hardware co-design approach, and for this to work well, we need to be able to quickly use a new instruction that gets added into the ISA, into the software to see how it performs. So to not make the compiler a bottleneck, we have a system of generating all the table gen instruction files directly from our ISA specification. So for each instruction in the ISA, we'll generate a class that will, so it's a class that will contain the assembly string, the input and output operand, all the bits, everything that you need to be able to generate an assembler at least. Also, scheduling information will be generated automatically. And then in a separate file, we'll add definition for each of these instruction if they're not already manually defined somewhere else. So this has 2 advantages. The first one, as I said, that's the main objective. It gives us a fully updated assembler, at least, that people can use directly to to test new instruction, try to use them in new piece of assembly to see if it accelerates some workload. But also this last bit of defining only if it's not manually defined means you can have some instructions which are automatically generated and some that we generated by hand, where we'll have proper lowering so that we can target from C++ code. One of the cons, it's based on our ISA specification, which is not public, so that this would not be suitable for upstream. But fortunately, as I mentioned, one of the pros is that we can have a mix of manual and automated definition. So if somebody wants to use a system like this, they can use manual definition upstream, and downstream still use the system to generate anything else that's not upstream. That's all for my talk. If you have any question or feedback about what I expressed, what I mentioned, please add a question on the issue queue on the GitHub repository for this conference, or you can contact me by my email there. I'm also hanging out on Discord. Not sure what's my name. Thomas Prodom, Thomas P or THOPRE. Not sure, but you'll find me. That's it. Thank you.
Great. Thank you so much for your time, Thomas. It's great to hear from Graphcore on their use of LLVM. Definitely echo some of my experience working on XLA, which was the JIT compiler in TensorFlow targeting the TPUs at Google here. Cool. So we have another 15-minute break. So we'll use that time after. When we rejoin, John Erickson will be joining us from Obsidian Systems. Is going to give us a really interesting talk about LLVM Toolchain in Nixpkgs. So I think this is going to be a really interesting talk. So make sure not to miss it. And we'll be back in 14 minutes. Thanks, everyone. Maybe I'll put on some light jazz for everyone too. Sorry, I just got reminded that we probably should find some unlicensed light jazz music to play. Let me see if I can find something else. Welcome back, everyone. Sorry for the trying to provide some light and entertainment there during the break. Our lawyer Katzen informed me I actually don't possess the license there, and I think the RAII is going to have to sacrifice some kittens now or something and try to take down the recording. I don't know. We'll see. Anyways, up next, John from Obsidian Systems is going to be teaching us a little bit more about how LLVM toolchains are packaged in Nixpkgs. John, are you ready to go?
Think so. Just pushing the present button. Wait, I have to push. Okay, is it showing up?
Yeah, looks great. Take it away.
Okay, great. Well, glad to be here. We can talk about LLVM Toolchains and Nixpkgs. It says on the tin. Joining me somewhat last minute is Lucas. Are you there too?
Yeah, I am.
Great. So I hope I'm not even going to attempt your last name, as I've just known you as Sterny on GitHub until now. But through just a little brief background, I use Nix at work. We do a bunch of Haskell too. Nix has had a long overlap with that, but I try to do all the languages and all the things. About 5 years ago, at the same time as I first started this job, we got really serious about getting some attempts that weren't really out there in Nixpkgs to make cross-compilation really good and get that over the finish line. I'm pleased to say it's been a great success. We can cross-compile all the things. We've had wonderful people come out and contribute, fixes to individual packages. And Sterny Lucas has been, in recent years, one of the biggest contributors there, and with the core infra. And really, I've been waiting for a talk like this and trying to present our work to a larger audience, because so much of this packaging work overall boils down to how the compilers and tool chains are packaged. This is sort of the initial generating decisions that affect everything else. But most people don't write compilers, don't package them, just work on their own stuff, and so it can kind of be a little bit obscure to most audiences. So I figured this is really the perfect opportunity. And LLVM in particular has really been our best behaved compiler. It does so many of the things I've wished, and in the case of GHC and some others, been trying to make them do things we want to see. So really just a big round of applause for LLVM for leading the way and out of the box getting so many things right. So yeah, we have way too many slides for 15 minutes, so I guess I'll, without further ado, go into the talk itself. So I need to say a little bit about the Nix ecosystem and how it works. I doubt this is really going to make sense, but there should be links and other resources. I'm happy to take questions in the GitHub issue, as Nick has mentioned. So layering, we have Nix, which is our build system on the bottom, and Nixpkgs, which is our humongous repo of all the packages on top. Nixpkgs uses Nix, and Nix tries not to know anything about Nixpkgs, not to do layer violations. So thinking more about that, Nixpkgs is where all the interesting things happen. It's quite complex, but evaluating Nixpkgs should be very cheap. Nix executes the build plans, which should be as boring as possible, as simple as possible, and also expensive, because that's when the actual compilation and other work's happening. So this division label should remind people working on LLVM and others of, let's say, CMake and Ninja, or Chromium, GN and Ninja. It's certainly not a division of labor we made up. But there are some things, nonetheless, that make us a little bit unlike those. It's best to start with Nix here. So the build artifacts are not just files, there are these other things too. And most importantly, we don't, with like Make and Ninja, unlike those, we don't choose where things go. Every build artifact gets its own fresh paths that take that yellow form for as many outputs as it provides, and everything is installed there very simply and dumbly, and that means you have to be really good about like not having a sort of coherent file system hierarchy standard type view of the world, because everything, all your inputs are going to be these paths that each have their own sort of mini FSH or really whatever you want inside, and you have to work from that. And the sandbox means you can't cheat. That really is what you'll see. And as a consequence of all this, there isn't really a global view. Every build just sees its inputs. There's no one build being more privileged than others. And so this keeps you on your toes, but also really helps something like cross, where normally the issue is like, oh no, we're not doing native compilation. All our assumptions we usually have been validated. Versus for us, it's like, well, we never had that many assumptions to begin with, so hopefully this can be less of a special case. I should say a little bit about Nixpkgs. That's less important in this talk. It's a big functional program. It works on the package granularity versus, let's say, Bazel's Bucks with their nice make rule effectively granularity. It's self-contained, so as much as is legally possible, we try to make everything download from source. Very few pre-built binaries, download those automatically if possible. We like Homebrew now, as Carlos was talking about, support Linux and Mac OS. Mac OS we can't be as good as in Linux, but we try to get close. So there is no like install Xcode first, however that's done, and cross your fingers. It's only download things and only peek at things that are installed in the system by default. And then a last thing that's very important for getting this whole cross thing going, Nixpkgs both contains the packages and our sort of functional abstractions that keep everything organized, which means it's really easy to iterate on both simultaneously, which was extremely necessary to make this cross-compilation stuff take off at all. So now cross-compilation in Nixpkgs. I've tried to make a little list here of the various axes of variation, but basically we try to do everything. We can't see it at all. It might be breaking, but the attempt's there, and if something does break and you need it, you can usually fix it pretty easily. Stuff like the architectures is pretty basic because it's the same packages. For me, the really interesting one is if we're trying to do different OSs or different libcs or something where we're like switching packages and switching authors and sort of going to a different ecosystem than versus the architectures of the variation each upstream ecosystem already tries to support. Of course, for like the embedded ones like AVR and Video Codec 4, you can't really build any packages, but you can at least build the Toolchains. And for the other ones, like full-fledged normal-ish systems, you could actually build a bunch of stuff, and people have cross-compiled whole systems. So yeah, we try to sort of split the difference between the super embedded, the sort of embedded Linux Yocto type world, and then like cross-compiled Debian or something really standard and run-of-the-mill. And have our dip our toes in every camp. So then the big question is, how do we manage all this complexity? I should start with recapping the GNU terminology for cross-compilation platforms. There's a build platform where stuff is built. That's the easy one. The host platform where stuff runs. There the naming's not so clear. And then the target platform is a really weird one, which is where stuff produced by this package runs. Thankfully in LLVM, the whole ecosystem is multi-target, so we can sort of stop thinking about the weird target one like the others and just worry about where we build it, where we run it, and just sort of what we do all the targets. But certainly we started this work with GCC. We have other weird packages. We were not so lucky to make those simplifying assumptions in Nixpkgs. So those gory details still bedevil us. And then, so it's good to think about, you can look at sort of whole systems, whole plans when you actually build something in Nixpkgs, which is very nice. You can just sort of bootstrap whatever you want, quickly build it, and it might fail, it might not, but at least it's sort of a coherent plan. But trying to like individually manage those would just be a huge amount of complexity and conditions. So it's also nice to think about a single package, a single function of its inputs, and as a very abstract model where you don't quite know what compiler or libc or whatever is being passed, and you're trying to, as simply as possible, handle all the combinations the whole thing might throw at you. And so the tension between these is, I think, sort of where design comes from. So with the unresolved in mind, the sort of first challenge with cross-compilation is just many sort of dependencies. We already had library versus executable. We already had build time versus runtime. And now we have to manage these different platforms in whatever form they take. So how might that be done? And the key insight here is that the platform should be thought relative package. So you shouldn't really think about your whole distro's build and your whole distro's host and your whole distro's target. And then instead think sort of the things I have in quotes. So if I need a tool, its host platform is going to be my build platform, a build time tool, because I'm going to need to run that thing. So I need to have the right host platform. And if that tool is some sort of compiler, and let's say it's a single target one like GCC, I'm going to need that tool's target platform to match my host platform. And so these sort of must be true equalities really cut down on all this possible complexity in the previous slide and make things a lot more tractable. Also, as it works out quite magically, you can just kind of make these local decisions every step of the way. Just with the idea in mind, I'm going to depend on it as little as possible. And a lot of the bootstrapping takes care of itself automatically and inductively. So that's been really nice that we don't have to like top-down plan the bootstrap order. It just sort of emerges from the requirements. From the entire plan view, this ends up looking in these sort of stratified stage package sets. So you can imagine the orange.
Do we lose control of the slides here? Sorry about that, folks. I think John might be rejoining here. May have lost connection.
Yeah, he's rejoining. He lost power apparently or something.
Special thanks to John, because this way I won't be the first one to have problems during the presentation.
It's got to happen to someone. It's inevitable, right? I think we'll probably reschedule the rest of the talk, I think during the break, that the breaks are kind of intended to have some flexibility time kind of thing there. In the meantime, while we're waiting to hear back and get John back online, Hans, can you start prepping your slides?
Yeah, I'm ready to go. Should I start presenting?
Sure. Why don't you go ahead? And I think when John comes back online again, you might have a slight interruption there. But I think if you start presenting, it'll take presenter. So can you give that a shot?
Let's let's give that a try. All right, can you see it?
Looks great. Okay, take it away.
All right, okay, so hello everyone, my name is Hans. I work on the C++ toolchain team for Chrome, which means I get to work on two great open source projects, both Chromium and LLVM. And I'm going to talk about how we build, test, and distribute Chromium C++ toolchain. So yeah, to start off with some confusing terminology here, people often ask what's the question, but what's the difference between Chromium and Chrome? And Chromium is that's the open source project where we develop all the code for the browser, and then Chrome is that's the browser project, the browser product that Google releases, and the difference is mainly the Chrome specific branding, and I think there's also a few video codecs in there, but yeah, the code lives in the Chromium open source project, and I'll probably be like mixing up these two words in the presentation. So how do we use LLVM? Well, we use it to build the browser, obviously. So we build Chrome with LLVM for all platforms. That means we use Clang as the compiler, we use LLD to link, we use libc++, the sanitizers, Clang format, Clang tidy, all the good stuff. And this goes back to 2009 when we started experimenting with Clang. I think the initial idea was looking into using it for static analysis and custom warnings and maybe refactorings and that kind of thing. And it turned out that Clang was a great compiler. It was fast, great warnings, all that stuff, and our compiler, our developers really liked it. So as time went on, we've been switching to Clang everywhere. It started with switching the Mac builds in 2011. Later, we switched to Linux and then the Android builds. And then in 2013, we started this big project to add Windows support to Clang with the goal of being able to switch away from MS Visual C++ over to Clang for our Windows builds. And we achieved that goal in 2018. So in Nick's words, it's like we've been shoving coal into the boiler for 12 years. That's where we are. Okay, so we're a browser, but how does that make us an LLVM distributor, which is the topic of this conference? Well, so the way this works for our developers is that once they check out the latest Chromium code, they run a script it's kind of like a post-checkout hook, which downloads third-party code projects, kind of like Git submodules, except like homegrown, and various other things. And among those things is that it will download the toolchain that we provide. So we provide, that means we're distributing it to those developers. And we're also distributing it in that way to all of our build infrastructure, which is a huge amount of machines doing continuous testing and also producing the builds that we eventually end up shipping. So in that way, we're distributing this to lots and lots of people and machines. There's also lots of Chromium developers outside of Google, both people working on Chromium itself, but also at other companies who use this to build their own browsers. So yeah, and we provide the toolchain for that too. And what we do provide is we provide the toolchain binaries on Windows, Mac, and Linux. And because we have these handy binaries, which are which are generally well working and close to the tip of tree, unrelated developers like not related to Chromium have found these binaries useful also. And in which way are we special then? So a few things that we think make us special are that we truly try to live ahead. We do frequent releases. So while LLVM Upstream generally does 2 major releases and 2 minor releases every year, we try to release every couple of weeks or so and stay as close to head as possible. And the reason for that is basically twofold. We figured like updating the compiler is a lot of work anyway. And if we try to do it gradually, maybe that's roughly the same amount of work as doing like a big one every once in a while. Not sure how true that is, but that's part of it. And the other part is, of course, that as we do a lot of development upstream ourselves, we do want to get those changes into our build as soon as possible. So staying close to head is that's the way to do that. Another thing that's special is that we try really strictly, or we don't try, that's how we do it. We're really strict about not having any local patches. So the toolchain that we build is truly, we check out the sources from upstream, and that's what we build and package. There's no local patches. Another thing is we're targeting a lot of architectures and platforms. So we target everything that Chrome ships on, which means Linux, Mac, and Windows, and Android, iOS, Fuchsia, and this means x86 and ARM, and a few others which are we also works but are less well supported. And the last one is that we're not unlike like a Linux distribution or Mac or so on. We're not like a general purpose toolchain for that platform. Really, our purpose is to build a Chromium browser, which means if that works, then we're happy. I guess this allows for a shorter qualifying period. We also have to make sure, though, that all the sub-projects also work, both as part of the browser, but these projects are also built individually and as part of other projects, like V8 is part of Node.js and so on, and that needs to work too. For example, our toolchain doesn't need to build everything that goes in a Linux distro, for example. So how do we do it concretely? The build is a bootstrap build. We start off with the platform compiler, if that's GCC or Visual Studio or Xcode Clang, and then we build Clang, and we use that to build itself in a bootstrap fashion. We use PGO and ThinLTO for speed. I think George has a talk about that later today. ThinLTO we don't do on Mac, but we're hoping that will become possible one day with the new LLD Mac port. And again, we build on Windows, Linux, Mac, both x86 and ARM64. And because these builds are fairly slow to produce these days, especially with all the bootstrapping and ThinLTO and so on, we have a cron job that provides us with fresh binaries in the morning, that's a nice way to start the day off for us. And hopefully we can end up releasing with those binaries and don't have to spend the day waiting for new ones. So that the testing is really the interesting part in this whole story, and we spend a lot of effort on that, obviously. So what we have is we have this tip of tree continuous integration build bots, the TOT bots that we call them, and what they do is that they continuously build tip of tree LLVM, Clang LLD and all that, and then it uses that to build the tip of tree Chromium revision, and then it runs Chromium's test suite on that. And we do that across all the build configurations and targets and platforms that we care about, which means it's a whole lot of build bots. Plus additional testing that when we actually check in a compiler release, we go through the regular Chrome test pipeline. So that's the testing that we do. And the whole point with this is to catch errors early. And then the actual distribution, what we do concretely is that our builds produce the regular tarballs, and we upload these to Google Cloud Storage. And we never delete anything. So if you're looking for an archive of lots and lots of old Clang versions, we have them there. And then we also push the binaries to our distributed build system so that it's ready to use this for our builds. And once that's done, and we put we're done with all the testing and so on, the actual update happens with a regular commit to the Chromium repository, where we update this post update hook to point it to the new compiler tarballs. So here is a summary that describes the whole process. It starts out with the trunk LLVM at the left end, where you might be committing something. That's going to get picked up by our continuous integration system at the top very quickly, and if there's a problem, hopefully we'll spot it. If things go well, and this happens every other week or so, we will release a toolchain based on this, the tarball there in the middle, and that gets used immediately by all our developers, all our testing infrastructure, and also the infrastructure that produces the production builds. which means so we have this for users who really want the bleeding edge version of Chrome, they can subscribe to what's called the Canary channel, and that goes out daily. So this means that depending on the timing, a commit that lands in LLVM, if it does that right before we cut the toolchain release, it could end up going into this Chrome Canary channel a day later. So we're really living on the bleeding edge there. So that's how it works, and these are my thoughts on things that could maybe be improved. And I've heard these some of these things echoed by others already. So maybe there's a good chance we can get somewhere else. So staying close to head, it's a lot of effort, and this in combination with our no local patches policy, and also we run the tests as part of like the LLVM and Clang test as part of our packaging, and we don't allow any test failures. This means that all breakages, they can slow us down a lot. Like even a simple lit test failure that forces us to repackage. So we really want to catch those early, and ideally we don't want those to happen at all. I met someone at an LLVM conference who was frustrated, saying it's really hard to get a patch into LLVM, and like once I finally do that, you Chromium people come and revert anyway. And I hope people don't feel too badly about that, but so this is the motivation that we try to catch things really early and revert, because having a stable LLVM trunk is important to us, and I think to a lot of other people also. So something that could be better could be if the upstream trunk was more stable in general, and I'm hoping maybe some of this can be achieved through better pre and post commit testing. We already have all of the build bots. We already have a little bit of pre-commit testing on Fabricator, but I think all of this could work better, because we still see a lot of issues where someone commits something that maybe passed tests locally on their Linux machine, and it breaks on Windows or Mac, or even just breaks on Linux anyway. And I kind of figure those such failures shouldn't really be a thing. Those things can be caught by machines before it lands in the trunk. And perhaps we already moved the version control to GitHub a few years ago. I'm thinking maybe leaning more into the GitHub infrastructure side of things with actions and so on might help with that. I'm hoping that there's a bright future there. Yeah, that's all I had. Thank you for listening. If you have any questions or comments, please add them to the GitHub issue. I'm also in the LLVM IRC channel and the Clang built Linux IRC channel on Libra. Thank you very much.
Awesome. Thanks so much, Hans. Yeah, it's definitely great to see, to see other contributors at least reporting issues upstream kind of thing. Is like, if you ever encounter an issue, sometimes, it's helpful to see, oh, someone else also bisected to the same breaking commit kind of thing. And so having those multiple reports is always appreciated. And, for sure, I look forward to the day that we can host additional infrastructure on GitHub kind of thing. I'm kind of envious of what the Rust compiler has, and Bohr's bots and integration and commit bots and commit queues, I think, are super helpful. And I apologize in advance to everyone who works on Windows. I've repeatedly broken the Windows build myself. I'm super guilty of that. So
we all do it.
Yeah. John, if you're online, just a quick logistic thing, if you don't mind, will we be able to reschedule the rest of your talk during the upcoming break? Does that work for you, John, if you're online? Okay.
That's great.
Perfect,
Sorry
thanks.
about that.
Oh, no worries.
Cut off.
It is bound to happen to someone, right? So don't worry about it. Great. Okay. Up next, we're going to hear from our friend Barrow again. This time, Barrow's switching hats, and he's going to be representing OpenMandriva. Barrow. Oh, sorry. It's Barrow's dog is going to be presenting, I think. Okay, take it away, guys.
Unfortunately, there has been a change in plans, so we are not going to talk about OpenMandriva. Instead, we have a much more important topic, which is how to chase a cat on a tree and keep it up there.
I approve.
I hear people voted against that, so let's get back to the OpenMandriva talk. Just a second. Okay, is it working? No. Should be.
Yeah, looks great.
Yeah. So first, a quick introduction. OpenMandriva is one of the older Linux distributions still out there. It dates back to the times of the 1995, 1996. Back then it was called Mandrake, and then later on, because of trademark issues, renamed to Mandriva. And then when the company behind it went bankrupt, it was transferred to the community as a pure open source project. And since then, it's been called OpenMandriva. It's a Linux distribution that is focused on the desktop. More recently, we've also added new targets like ARM and RISC-V. For example, the PinePhone is an interesting target, and a couple of dev boards, BeaglePi, FrogPi, Raspberry Pi. And we are also building images for servers and virtual machines these days. That's a little bit much to do, but we found it's actually less work to make our stuff suitable to run everywhere than to have to maintain different stuff to keep our infrastructure running. So it's an independently developed distribution, not based on any other distribution. But of course, if we see some other distribution doing something interesting, we won't hesitate to borrow it or steal it. And we switched to Clang as our main compiler as early as 2015, which is one of the reasons why we've decided to be independent of other distributions. Only that enables us to do moves like that. If you're interested in more details, check out our websites or look at the communications channels mentioned on the last slide. So why did we decide to switch to Clang back then? Primary reason is that we like readable and maintainable code. GCC is great for users. We still don't have any problems with that, but it's not so good if you're working with its code. And essentially, Toolchain maintainers are lazy people. We like to work with code that we can understand. We also expect targets like AMD GPU to become increasingly important. We don't like duplication too much. We need LLVM anyway for things like Mesa. There's some useful tools like sanitizers and C-reduce that at the time were Clang specific. In the meantime, GCC has been catching up a little bit, but Clang still is a little bit ahead. And usually there's not a lot of trouble with pre-release versions. So our idea is that our beta releases and so on should be similar to what we end up releasing. So if we know that we are going to release a final version after the release of Clang 13, we switch to Clang 13 snapshots and betas early. So our development tree has been on Clang 13 since RC1 was released. So the next interesting thing is what parts of LLVM we can use and what parts we can't use, and then why we can't use those. LLVM libraries in Clang, LLD, OpenMP, Poly, and libunwind are all pretty much unquestionable. We use those by default. We sometimes provide a couple of alternatives because some stuff doesn't work with them, but in general, those tools do a great job and are the default and used over anything else that does the same things. Then LLVM Min-GW is something we use a lot, but we have a wrapper script. So if you look at our user bin AR, user bin NM, and the likes, it's neither the LLVM version nor the GNU version. It's a script. Why are we doing that? We have both Clang and GCC. And both compilers support LTO. Both compilers' LTO files are not object files that anything would recognize. So if someone is using GCC with LTO enabled, the LLVM version of Min-GW will not be able to handle it. And if someone is using LLVM with LTO enabled, the GNU version of the Min-GW tools will not be able to handle that. So what we do is put a wrapper script that first checks the input. If it sees any GCC LTO files, it passes the command on to GNU Min-GW. And if it doesn't, so if we are using LLVM LTO, or if we are using compilers without LTO, it goes to the LLVM tools by the same name. PGO is something we've started using for some key libraries where it's easy to generate useful profile data. For example, things like libjpeg, libpng. We generate profile data by converting a couple of desktop backgrounds. This is at the moment disabled because of LLVM bug 51624, which I hope will be fixed before the LLVM 13 release. We expect to extend PGO to more packages. The main thing in the way of that is obviously having some way to generate useful profile data that actually matches what users will do. LLDB is included, is actually a recommended debugger, but GDB is also there. And according to our download statistics, most people still use GDB simply because it's what they're familiar with. LLDB is doing great, but people are a bit reluctant to learn using new tools when they are a bit more different from what they're used to. Compiler RT is something we used to enable by default, but for the moment we've had to switch back to libgcc because of a couple of corner cases. So if we had built one library with GCC, therefore linking that to libgcc, and another library with Clang, therefore that library is linked to compiler RT, and then they're used in the same application, and something calls into a compiler RT or libgcc function that can cause problems. So for the moment, we've switched back to libgcc there, but the plan is to switch back to compiler RT once that problem is really solved. libc++ is a bit of a problem. We really like it. Our benchmarks shows it mostly outperforms libstdc++. But at the moment, we cannot really use it because binary compatibility with other distributions is a topic. So if we build our system libraries like Qt against libc++ and a user installs a non-free application like just about any game on Steam or so that links to Qt built with libstdc++, obviously that's going to cause problems. We don't want to duplicate all system libraries. So for the moment, we are using libstdc++, but we hope that will change in the future as well. Since the main problem there is binary-only applications, if it's open source applications, we can just rebuild them ourselves and add them to the repositories. This might be fixable by more applications moving towards Flatpak or the likes. So it remains to be seen how much longer we will depend on binary compatibility with other distributions. And obviously, in the ideal world, by tomorrow, everyone will start using OpenMandriva instead of other distributions, and then everyone will use the libraries we are providing. But I don't see that happening anytime soon, so we'll probably stay with libstdc++ a bit longer. Then LLVM libc is not really usable yet, but we are watching out for it. It will likely have the same compatibility issues that we are seeing with libc++, so it probably will not be our main libc even once it's really ready. But at some point, if it turns out well, we will almost certainly do a different build that is based on LLVM libc and libc++ to see if it's worth doing from a performance perspective. And if it really outperforms our regular builds, we will find some way to make it work, even if that means packaging some extra libraries that binary-only applications can access. So we make a couple of modifications to LLVM in our packaging. Most are not complicated. We have some minor tweaks like adding the target triplets, changing a couple of default settings. We backport a couple of patches from the master branch and from Fabricator. Most notably, at the moment, we are taking the RISC-V linker relaxation patches. Then we copy in the SPIR-V toolset, the SPIR-V LLVM translator, SPIR-V headers, SPIR-V tools into the LLVM source package, just to make sure the SPIR-V LLVM translator is always in sync with the main LLVM tools. Another thing we have to add manually is cross-compiling compiler RT to various architectures we want to support. That's a little bit of a problem upstream. If you build LLVM and you say enable all targets, you get a nice version of Clang that will give you an ARM binary. If you say Clang-target ARC64 Linux or whatever, but if you try to use anything that makes sense, it will complain about the runtime libraries not being available. And cross-compiling them is not totally simple. We found a way to do it. If you're interested, look at the LLVM spec file in OpenMandriva. But that would be nice to integrate that better into the LLVM build system. And then there's one change that is probably a bit controversial. We changed the default value of -f GNU-C -version, which is 4.2.1 in upstream LLVM, to 11.2. Why are we doing that? We found in quite a few packages there's code that checks for GCC version, and if it finds a newer version, sometimes it's newer than 5, sometimes newer than 8, sometimes newer than 10. It calls into a fast version of a function, and if not, it calls into a slow version that will even work with an ANSI compiler from the 1970s. So if we leave GNU-C version at 4.2.1, we will often get a performance penalty, and we won't even notice because nobody really checks all the code. This really shouldn't be done, but it's everywhere, and as a distribution, by definition, we deal with third-party code. It's not our fault that the code is there, so we have to deal with it. We are not in a position to fix it. Even if we fix it in a couple of cases, there's no guarantee the patches will be accepted upstream, and it will just be back to the more of the same once we update the package again. Of course, this also causes problems, because sometimes there's a check for the GCC version that really calls into a GCC-specific feature. And if it's on an older GCC, it would call into a function that works with Clang. We get this on a couple of packages, but we prefer this breakage over just not getting the optimizations, because this will result in a compile failure. That way we will see what's going on, and then we can add a workaround like appending -f GNU-C version equals something lower as a quick fix, or even fix the code. There's a couple of packages where we have to resort to another trick, which is using export cc equals GCC, export cxx equals G++. We don't consider that a taboo. While we prefer Clang, we don't hate GCC. But this is down to a handful of packages. Back in 2015, when we started using Clang as the primary compiler, it was a list of about 200 packages. Now it's down to less than 10. glibc is a big pain that contains a lot of GCC-specific code, and I don't see that going away anytime soon unless someone puts a real effort into it. We have a problem with grub2 where the theme engine doesn't work when built with Clang, so that needs to be debugged at the moment. Just using GCC is an acceptable workaround. PPL has a compile time error. Wine has an error where Wine CFG crashes on startup in 64-bit mode if it's built with Clang. With Mesa, we have a fun problem. It works generally when built with Clang, but some people with old CPUs reported crashes on startup, so we suspect there's some way SSE3 or something higher can leak into the code, even though there's no -mRch switch allowing it. And we have a similar strange problem with systemd on x86-64 hanging on upgrades if it was built with Clang. And to make it even stranger, this happens only on x86-64 generic, but not when targeting Ryzen CPUs specifically. So that's some weird stuff that just has to be debugged. And then probably at some point we will get that package count down to 1, that one package being glibc. Now, that's the update on the use of LLVM in OpenMandriva. There's obviously more things to talk about, but nothing we can fit into a lightning talk. So if you have any questions, if you're interested, if you want to help us out with anything, go to the slide deck and look at the various communications channels mentioned there. With that, let's go back to the next presenter, which
Awesome.
will once again be Laska talking about chasing cats on trees.
Woof. I think was it Plumbers last year? One of the conferences, was it the LLVM one or Plumbers for the kernel? They actually had a session for pets, of everyone show off your pets, and that was a really fun a fun chat. But anyways, thank you so much, Barrow and Pup. I always look forward to these reports on how many packages we still need to work through and churn through, kind of thing. And I wouldn't count glibc out, kind of thing, but it's definitely probably one of the larger remaining hurdles, kind of thing, for sure. So thank you so much for your talk. And up next, Serge is going to join us from Red Hat, and Sylvester, who is representing his work both on Debian and Ubuntu. And they're both going to present work that they're doing on a integration test suite for LLVM. If you guys are ready, please take it away.
Yep. So we are trying a strange dance between Sylvester and me. So let's see how it goes. So I'm Serge, working on LLVM both upstream as a developer and downstream as a packager for Red Hat and so for RHEL and Fedora.
And I'm Sylvester. I have been maintaining the LLVM toolchain for almost 10 years in both Debian and Ubuntu. I also created and now maintain apt.llvm.org. My paid job is at Mozilla, where I'm working as a director. If I'm mentioning that, is to highlight the fact that it is completely unrelated. I'm just a geek and doing that on my weekend and the evening. So it's not a Mozilla project. And so how did we start that project? So to verify that I'm not breaking anything in Debian and Ubuntu, I have something like an ugly script of 2,000 lines of code, and I was sick of it. I'm using it basically to verify that either if the chains are not going to break anything, if that all the combination of options is still working. When I fix some weird issue and I don't want that to regress, and when it is distro specific, I'm going to add that in that file and so on. So it produces a lot of checks, but it's very Debian specific. And Serge had also similar checks for LLVM into Fedora. And during the lockdown, I had plenty of time in the evening for a bunch of reasons. And with Serge, we were joking about a bunch of things. And one day we were complaining about the duplication of the work that we are both doing. So we felt that it was dumb that Serge was doing something and I was doing exactly the same in Debian and Ubuntu. And we were like, oh, what if we start working together and try to start a new project so that I can work for Fedora and Red Hat, and Serge can help me also with Debian and Ubuntu. So that's how this project started. So now, what is the goal of that project? To be more clear. So we really want to make sure that the LLVM toolchain works well together. So a simple example, which sometimes it breaks, is that Clang using LLD as a linker, providing LTO, is still going to work if I make some stupid changes into the packaging. And we want that to be consistent. So that means that if I am an upstream developer, when I say upstream, let's say that I work on Firefox and I want to build it on Fedora and on Debian, I want to make sure that this option works well when I use Clang. We are also working on the packages, which is quite unusual for software. We don't have access to the sources or the object file. We really want to test only the binary and the packages which are installed through the packaging system. We are also trying to bring consistency over the packages. So as a user, it's always a pain when packager make different design decision with where the header install, how the program should behave. So thanks to that program, we see that as a forcing function, so that any user using Debian and Ubuntu, if they move to Red Hat or Fedora, they will get exactly the same argument and pretty much the same behavior. Because I'm not talking about Serge, but myself, I'm quite lazy and I'm always frustrated when I regress or when I'm fixing bugs that I fixed 6 or 7 years ago. So I'm trying to make sure that I'm preventing myself from making the same mistake over and over. the goal of that project is to help you folks, other packager, to leverage that to make your life easier. And last but not least, to provide an easy behavior close to make this check in the automake world. So now Serge is going to tell you a bit more about how it works.
So from a pragmatic point of view, it's a CMake-based project that basically inspects the environment and checks which binary are available. We don't want to hard-code this list of binary because it depends on the system. For instance, on RHEL, we don't install all the LLVM toolchain. Some parts are missing. And we want the test suite to adapt to what is available to the system. So we do all these binary and library checks. And we are only going to test the one we find. And once the configure step is done, we run the test suite, which is lead-based, and some tests are enabled and some are disabled, depending on the configure step, much like it's done in the LLVM unit test suite. And we do plenty of tests, so checking whether we find the OpenMP library where we are supposed to find it, checking if we can still build plugins for LLVM. So are the headers where we expect? Are they installed correctly? Does LLVM config point at the right location? All this kind of stuff which are not tested at all by the LLVM inner test suite. So that's not unit test, that's really integration test. And we try to feed them. Next. So one example of a test, it's a lead test you all know and probably like. The requires line are very important because of this portability of the test suite based on the environment. So whenever we require some headers, some binary, we list them in the requires section. And then we just run the regular test, performing whatever integration test we want, trying to keep the test very simple because we want them to work across LLVM versions. We want them to work across a different distribution. So nothing specific, just what the user expects and nothing more. All the tests are done through GitHub Action. Currently, they are only run on Ubuntu. So we are, from the GitHub hooks, they are only run on Ubuntu in addition to the tests that run on Fedora, on RHEL, and on Debian. But for the CI, we only run on Ubuntu, different version. The fact that it runs on different version helps us not having something specific to a given LLVM version, which tends to be a good property, even though we could have we could leverage the requires feature to require a given version for a specific test. But we want to keep it as generic as possible. So what do we test? We test many, but definitively not all of the LLVM tools or LLVM utils. We test Clang and its integration with both the GCC toolchain and the LLVM toolchain. So that's both for the compiler runtime, for OpenMP, but also for the sanitizers that have a runtime requirement. So sometimes Clang may not find them if the packager does not install them in the expected location. So we check that. We do check some Clang tools like the scanner, but not all of them. Probably LLDB, LLD, and whether LLDB works correctly on debug info generated by GCC and the other way around. Whether we can compile with GCC and link with LLD. So there are also some tests for integration between GCC and LLVM because that's a use case for the user. We do also check the LLVM plugins, whether they can be compiled and loaded correctly. which test LLVM config. We do a bit of test for lib and wine, but not that much. It's not packaged yet in Fedora. And compiler-RT, which is a requirement for many options. But more importantly, there are things that we don't test. And we try to avoid, well, even though Sylvestre tried to sneak in a lot of Debian-specific stuff into the test suite, just to have me maintain it for him, I'm trying to refuse that and have only distribution-agnostic tests. So if Debian installs something and we don't, we add a require. If Debian has a specific installation path, we don't hardcode that in the test so that it also works on Fedora. And that way we can hope that it also works on any other distribution that would want to adopt this test suite. We also don't track LLVM IR changes or whatever could be different across version or very specific to, I don't know, the evolution of the C++ standard, this kind of thing. Those are unit tests, and they are already well tested within every independent project. So we don't focus on that at all. And after the hard work by me, the success described by Sylvestre.
So yeah, we have other successes with that project, but I'd like to highlight two of them. So the first one is a regression that I caused a few days ago. It made it to Debian. I was playing with LLVM runtime option and making a mistake doing a merge. I removed binutils include dir option, which, as its name is not clear, it's enabling LLVM Gold. And I noticed that thanks to the test suite, because it didn't fail during the build, but the LLVM integration test that we wrote with Serge identifies that and catch it. The other thing is I saw during the previous presentation, some people highlighting the fact that they are either patching or not patching LLVM. I'm lazy, as I was saying earlier, so I do patch heavily LLVM toolchain. So in some cases, I'm just going to hardcode passes. So for example, when I package a scan build in Python, I hardcoded some passes. And Serge last week reached out to me and say, how do you make it work? And I was like, oh yeah, I have a patch just to hardcode the pass. So Serge, being less lazy than I am, he fixed that upstream. So now, thanks to that project as a forcing function, it is now working out of the box. So I see that also as a way for packager to be forced to do the right thing when they are not doing a great job like me. So in terms of status, so it is deployed and used in Debian and Ubuntu in production. So if you look at the package being built on those distros, you will see that those test suites are executed, and they are going to break some of the migration step in those distros. I'm also running them on apt.llvm.org, and it's used also now for Fedora and Red Hat. Serge was telling me that it helped identify some recent regression recently. So next step, one of the things that we would like to get at some point with Serge is to see if people from the community would be interested into merging that directly into a LLVM project. We are convinced that it makes sense. We are already representing 3 major distros, but we would like to get also other users. For example, it would be amazing to have that in Homebrew to demonstrate the value outside of the Linux world. One of the things that we would like to get is also starting to test more the LLVM runtime builds, in particular making sure that those options are enabled and correctly set, and we are providing the same set of features in terms of build, how it looks like. Add support for other libraries, MLIR is one of them. And myself, I'd like to start making more progress on decreasing the G++ dependencies, the GCC dependencies that we have. They are quite intertwined currently, so I'd like to make progress on that, and then add test to make sure that other follows. So giving more work to Serge in Fedora. So Serge, do you want to say something to conclude?
I'm a big fan of the automake disk check rule, and basically what we are trying is to offload that to a separate project, but I do think that it would be great for upstream, because that would share the load across not only 2 people, but more of them. And there are so many ways that different components of LLVM cannot work well together if we don't take care that it's good to have this kind of checks.
Thank you for your time. Don't hesitate if you have any question or if you want to contribute.
Great. Thank you both so much. That's such a fantastic story of collaboration together. Really, my hope is, if this conference proves useful to people, if we'd like to see another iteration of it next year, I'd love to have you get both back and see kind of the growth in this project, hopefully over the next year for sure. And my hope is, maybe we have a couple stories like that out of this conference. So thank you both so much for this talk.
And fingers crossed in real life. That would be even better.
Sure. Yeah. Will do. So now we're going to thank you again. Yeah. Now we're going to follow up with John again. We had some slight technical difficulties but we'll fix it in post. Don't worry about it, John. You ready to go with your slides again?
I think so.
Okay, let's try it out.
Okay. I think this was the slide I'm on.
Cool, looks good.
Okay, great. So yes, as I was saying, for the fortunate sudden laptop suspend, the runtime depths and the build time depths, the sort of difference between those sort of depths determines the bootstrapping. And this is sort of a miniature sketch of what an entire bootstrap plan might look like, or part of one, where we've got in one color, one stage where everything here relates via runtime depths, and in a different color we have the previous stage. And so in both cases, the solid lines are the runtime depths, and the dashed lines are these sort of build tool depths between them that have the sort of my host is not my build tools host situation from before. To then think back more on how these hosts and builds relate, rather than having a wall of text, we can do it pictorially. So here again, we have the stages. Each of these stages is a bunch of packages with the same build host and target. And then each stage that depends on the previous one, there's that sort of off by one thing. So you can imagine the host of the tool then becomes the build of the user of that tool. The target becomes the host, as I was saying. Also, I have a few slides with the same sort of color scheme. So get used to brown being build, turquoise being target, and then the ambient black being host. So yeah, when we're doing our normal native build set, we sort of make the stage, the single native stage, also the previous stage, and this sort of fixed point construction. And then because of these same equalities that relate, the tool depends and the host depends, that sort of forces everything to be the same, which it is for native. So there's a nice, the math and what you're trying to do works out. In the cross, we typically have 3 stages like this. So we have our normal native stage on top, our native stage but targeting something different, which will mean not rebuilding LLVM, but yes, rebuilding GCC in the middle. So it's sort of a mini stage. Most things end up being the same. And then our actual cross stage on bottom, where now we're doing a whole different thing. So then to kind of sum up that up, we sort of these ways of writing, both writing packages and filling out the all systems sort of makes it go. You can say with the functional programming terminology, elimination is bad. And I think the third mini bullet there is the main idea. Think like a symbolic or abstract interpreter. So really don't try to inspect what you've been passed, or do so as little as possible. So if you get something which is the description of the host platform, try to treat that as a black box. Try not to care if build equals host. And so these sort of, play hot potato with your parameters it sounds a little silly, but it really does cut down the complexity a lot. Likewise, native should just be the identity cross. It should be as little of a special case as possible. If you don't care whether build is the same as host, then it really isn't a special case. If you might optionally care, try to do that, as small a scope. And also, we never really did sort of the is cross sledgehammer. That would probably be fine in the LLVM ecosystem, but with all these GCCs and other things around, it's just an excuse to get your builds, hosts, and targets mixed up. And doesn't really fit with the others, but also I want to do a shout to Xerbo, which Salim, who gave the talk earlier, has worked a lot on. It was sort of the first distro I know of to kind of do stuff somewhat along these lines, so it's been a big inspiration. Now getting back to, we're here to talk about compilers and LLVM. So much of the complexity we had to do with the way GCCs work, and compilers like that. And so if we think about these Canadian crosses where build, host, and target are all mutually different, we get these really funny situations, which I'll try to diagram like that. So this is GCC. We have tons of compilers, tons of different stuff. Might need a little tool to generate the parser or some options things. There's a few of those. There's of course some new GHC. There's some linker, which is going to be remembered by GHC, the default one that goes in the -b directories. There's the runtime libraries, and so this is supposed to be confusing. It confuses us. There's too much going on for one single package. GHC, I mentioned briefly, I work on a lot of Haskell. I work on GHC sometimes. Exact same problems. You can just take the same boxes and change the text because it's just as bad. LLVM is much better. We have a little bit of fishy fishes with if you want a build time LLVM config, but with Clang, LLVM, and the main tools themselves, we can drop the turquoise box because they're all multi-target. Libraries, of course, don't even have a notion of target as they are not producing code. And it gets better because LLVM config is already semi-deprecated. I hope it gets removed and the ecosystem adjusts. So if you remove that, now we're even simpler, just a normal bootstrapping tool chain, which because it might be GCC or something, I do all the colors, the new tools, new libs. And if we assume, GCC is completely purged, Clang's all the way down, now we have no turquoise, everything's target agnostic, and sort of in the limit, all the bootstrapping you want, there's everything sort of nice and symmetric again. And so all the craziness of before is really gotten rid of without compromising anything. So this is the dream when cross compilation just becomes really easy, and we're excited to be getting there. So I won't click any of these links, but for anyone reading the slides after, I want to kind of point out where in the repo some things are. Besides the actual LLVM components being packaged, all in their separate packages for each library, notably. We also have these wrapper scripts, which are these kind of bash monsters, which assemble tool chains. It's listening to the other talks. This has been sort of a frequent difficulty for everyone, which makes me feel a little bit better. Yeah. So based on everything we've learned here, I think the #1 lesson is projects really should not insist on handling their own bootstrapping. And it's much nicer to have the distro always handle this in the same way. So for LLVM, that just means you don't have to do the mega CMake. You can build all the components separately. And then for GCC and GHC and other ones, that's, well, that just doesn't exist. The components aren't really meant to be consumed separately, and that's a big bummer. Again, try to make cross-compilation as the normal case and native as non-special a case as possible. And also the runtime libraries themselves, I like to think of it as they're just normal libraries that happen to be used by the compiler in a special way, which traditionally standard libraries come with all sorts of exceptions. And even beyond the build system, there's just weird assumptions and things. And LLVM, again, is really good with all these, but on the last one, yeah, it's a normal CMake build. You can already use the generic CMake, like don't test if the compiler works yet if you're building compiler RT or something. So yeah, we're really in good shape on all of these. That said, there's a few things that aren't quite perfect that I thought I'd give a brief mention to. So one, which I started, is adding GNU installers support to LLVM, which if you're not familiar, it means these sort of libders, includers, binders, other things can all have separate install paths. So like many distros, we want to separate the sort of meat of the package and the headers and other things, which you would only need at build time downstream. I don't know how most distros do that, but we, I think, atypically use the GNU installers for that. So as I mentioned, really at the very beginning, every build step for Nixpkgs, every package will have one or more outputs, which you give names here, and then you have assigned to you these fresh paths. And our just sort of generic CMake infrastructure will see these existing and pass flags like this, which notably are absolute paths that tell CMake these things go here, those things go there. Yeah, so I've been trying to get LLVM to support this out-of-the-box CMake thing, which is a little bit of work, but not too bad. You may be wondering why we want this. Of course, it's nice to do the normal splitting thing distro's always done, but then again, space is cheap. Does it really matter? I think the more interesting reason is we want to get upstream kind of aware of our use case without burdening it with all the idiosyncrasies. So for example, our putting everything in its own weirdly named subdirectory is not going to be very common, but just having these parameters for different install locations hopefully sort of makes the possibility of such things less odd, and gives it sort of, look before you break it, support upstream. So for us, it's kind of a way to kind of nudge, hopefully not rudely, on the stuff we do in a way that is useful to others. So I've done a number of preparatory patches so far. These are the two main ones now that the foundation's been laid. And thanks to all the reviewers we've had, and people who are talking today, Petar and Salim. So yeah, it's been great to really cut my teeth actually contributing to LLVM with the stuff. Second thing, and the remainder of these will be a bit more abstract and speculative. Clang has both -b and -resource-dir for specifying where certain distinguishing things goes. And it works. We've gotten everything to work in our upgrade scripts, but we can't help but thinking it's maybe a little bit more complex and idiosyncratic and sort of history of GCC informed than it needs to be. Like, do we really need a separate resource-dir, or could we just use -b? Or even more radically at all, do we really need any of these things? And could we just tell Clang we promise to be careful and just use the normal -l, -i, iSystem, iLocal, etc. flags, which it is scary to sounding, and regular users just using the compiler could cause themselves all sorts of grief. But back to that early principle of trying to make the runtime libraries sort of as normal libraries as possible. I don't know. Every time I see a special case that I'm not quite sure is carrying our weight, I just sort of look at all the complexity we have to deal with supporting all these targets. I think, is this really worth it, or is it better to just be consistent and risk some confusion?
John, do you mind if I step in real quick? Sorry,
yeah.
I don't mean to cut you off again, but I got to keep the trains running on time kind of thing. It's going to be time for our next talk coming up. Do you mind, and it shouldn't be a problem for us to schedule, like I plan on doing the thing in YouTube where you put like the bullet points so people can click ahead. So I can just slice in like part 1, part 2, part 3 kind of thing. Would you prefer to finish this up either during the lunch break or maybe after the scheduled talks?
Yeah, anytime's fine. Yeah, I'm sorry, I did not check the starting time when I went.
No worries, no worries. I think it's really great content, and you should have the opportunity to finish it. Why don't we follow up in the speakers chat on GitHub on either of those choices which you prefer, which works for you, kind of thing.
Yeah. Yeah.
Cool.
Absolutely.
Sounds good. Okay. Up next, George from Google is going to teach us a little bit more about using PGO on our tool chains. George, are you ready to go?
I think I am. Let's see if I can get the tab up.
Look at that microphone. Are you a professional streamer, George?
I try not to be, although I spend a lot of time chatting with my friends, like playing video games and such. So they all had fancy stuff, so I decided to have fancy stuff too.
Sounds great.
Cool.
Worthwhile investment.
So is this the right one? It is not. Let's try again.
We can see it.
This
there we
one.
Go. Yeah, it looks good.
Awesome. Cool. So as Nick said, I'm George, and today I hope to present on distributing PGO'd toolchains for great good. The idea here is that I like it when developers are happy. They sometimes feel more fulfilled. They use smiley faces in their messages, and they merge my PRs more often. Regrettably, there are a lot of things that make developers unhappy, many of which we can't really address necessarily technically. But one thing that we can address technically is slow builds. So I would like to propose that we make builds go faster with the requisite comic of XKCD whenever you're talking about build speed. So as a spoiler, PGO and ThinLTO, when combined, generally make builds about 13 to 25% faster. We see this both in the entire time that it takes to run like a Ninja on LLVM, and also when looking at like a singular compilation. So the one thing that I did want to bring up is that I kind of also mentioned ThinLTO here, whereas I didn't in the title. That is because I totally forgot about ThinLTO, but I wanted to still include it in the talk because it synergizes really well with PGO. So I'm going to be talking about them more or less as a unit within this talk, although they are different technologies, and they are they can be applied separately if you so desire. It's just that often it doesn't make much sense, which I will get to later. So as a quick description, what is ThinLTO? When you're building C and C++, you're often doing so as a series of compiler invocations on C and C++ files. And while the compiler can see and optimize across multiple header files, it can only generally see one C++ file at a time. So people came up with a thing called LTO, which is link time optimization, which makes the contents of basically all C and C++ files, which are being linked together, available to the optimizer. ThinLTO is basically people said, okay, cool. We can do this cross-module optimization. Now we can do this cross C++ file optimization, but that makes builds a lot slower. So we should be able to do this in parallel, ideally, so that a singular link doesn't take hours. That's ThinLTO in a nutshell. There's a lot of cool stuff about it, in my opinion, but that's kind of also outside of the scope of this talk. In general, you can do ThinLTO as long as your entire toolchain supports it, which all of Clang does, just by adding a singular compile flag. LLVM does this a bit differently, but I will get into that soon. So what is PGO? The idea is that many optimizations in Clang rely on guesses about how your code will execute in order to be effective. Which branch is more often taken, which code is hot, which code is cold. Sometimes it even tries to reason about, hey, this is like a virtual call. Where does this go the most often? LLVM has a lot of heuristics about these things. And PGO basically says, why do we have this heuristics when we could simply tell the compiler? So PGO is a bit more complicated than LTO from the standpoint of applying it. You need to build a binary that is instrumented so that it can tell the compiler which branches are taken, which branches aren't, et cetera, et cetera. You need to run this on a representative workload. And then you need to take the profiles which this binary produces magically. You need to post-process them, and then you need to rebuild the binary with those post-processed profiles. So like I said, this is a fair amount more effort than LTO in general, but LLVM tries to make it a bit easier. You might also note that representative is in scare quotes. I will get to that soon, because there is a bit of discussion to be had about like, what should I actually run my compiler on? So as I mentioned earlier, Clang makes all of this a fair amount easier. To apply thin-LTO to Clang, you pass a singular CMake flag and you're done. Like I said, the toolchain that you're building with has to support thin-LTO, but Clang does, and it was mentioned earlier in this series of talks that like, you know, generally you need to bootstrap and such. So you should ideally have a thin-LTO enabled toolchain. PGO, again, a bit more complicated. For profile collection, there are a few things that exist in the tree. There is a Python script which tries to be a one-stop shop of run this and it will do everything to build a toolchain which is fully optimized with PGO. You can also make it stop short and simply build a toolchain which is, or sorry, you can make it stop short and make it only build a single like profile. There's stage 2 PGO with CMake, which does very similar things, except it's entirely within CMake rather than being a separate Python script. And if you want to build your own profile, our CMake bits have the ability to build a fully instrumented Clang, which you can then drive with your own benchmarks. Regardless of how you choose to collect your profile, application of it is just as simple as thin-LTO. You pass in an extra CMake flag, and it gets applied throughout the build as it should. So I promised to come back to what a representative workload is. I work for Google. I work with many teams who ship toolchains with PGO applied. And each team kind of does a different thing for what its representative workloads are. Android, in particular, tries to build a few medium-sized targets in their code base with an instrumented compiler. They vary things between thin-LTO, they sometimes do like vanilla linking. They vary up the target because Android, surprisingly enough, cares a lot about ARM32 and ARM64. Chrome OS says, let's just build and link all of Chrome, which is very, very time consuming, but it works. The Chrome toolchain team appears to build a single very large II file and say that's what our profile is coming from. Once again, they seem to be successful with this. And the toolchain that we ship for our servers builds a few small targets and, surprisingly, protobuf files, because our servers care a lot about protobuf files, and the binaries that we ship include a lot of them. I think the critical point of all of this, though, is that despite how different these approaches sort of are, they're all quite successful. So I'd like to say that, like, when you're thinking of what benchmark should I actually apply for this PGO profile, like, I would almost want to say good enough is good enough. If you start with a Ninja, check Clang, check LLVM, which is what the machinery that I talked about before kind of does. It just builds some stuff within LLVM's tree with the instrumented Clang. That's going to get you most of the way there when it comes to PGO's benefits. If you have specific well-known use cases that you'd like to target, that's awesome. You're more than welcome to add those or tweak the benchmark part of your PGO pipeline as you prefer. But at the end of the day, the super low effort thing appears to get, like I said, most of the benefit. And I know that, at least in my case, I would often try to pursue the optimal 18% improvement, and I would get to it a long time from now. And from the standpoint of delivering things, I would much rather like say, okay, here's my 5 lines of script. It gets us a 15% improvement. Fix me, make better benchmarks in the future. So in summary, please consider PGOing and thin-LTOing your compilers. They're faster builds for users, and your future builds for future compilers will also be faster, which is an awesome sort of bootstrapping benefit. Happier developers worldwide equals my PRs are more likely to be merged, which makes me very happy. We try to make all of this pretty easy, but so there's even some discussion on the issue that I filed for this presentation about like, here's ways we can make it easier. I'm not sure that I'm the best person to push that upstream, but in general, LLVM upstream seems to be very receptive to like making flows like this easier. So if folks have ideas or thoughts or such, feel free to engage with the community on that, right? And as a final slide, I realize, and I mentioned earlier, that I sort of conflated thin-LTO and PGO here in terms of their speedups and such. So I did want to touch a little bit on when you use them separately. PGO provides most of the speedup in my experience between the two. But fundamentally, thin-LTO is a series of optimizations, and PGO informs optimizations about how to be more optimal. So I found that in practice, and other teams have found that in practice, when you use these two things together, the whole is greater than the sum of its parts. You will get a better speed up than using either one of them individually, which is why I said earlier that it doesn't make a ton of sense to use them apart. Maybe PGO is a bit much to ask for from some folks. But again, if you all know how to make it easier or have ideas, feel free to engage with upstream or chat with me, and I can try to help push that forward. And that is it for my presentation. So thank you all very much for your time.
Wow, so the part's greater than the sum of the whole. That is awesome. Thanks so much for those numbers, George, and the time and effort spent into collecting all those numbers. It's super helpful and hopefully illuminating for a lot of folks. So up next, we're going to have Amir's presenting a really cool optimization utility from Facebook called Bolt. This is something I've had my eye on for a very long time, and I'm super excited about its potential applications and uses. And I think this is probably a great place to demonstrate its benefits towards Clang. So Amir, if you're ready, you mind taking it away?
All right. Can you hear me?
Yep.
Cool. So first of all, thanks Nick and George for setting the stage for this talk. Let me share my screen.
Cool.
You should see. Okay. All right. Hello, my name is Amir. Today I'm going to present Bolt and how it can speed up Clang itself, which hopefully results in faster builds, which I guess is relevant for LLVM distributors. So the goal here is to explain how Bolt is able to speed up Clang and share some results. I'll start with an overview, then show usage examples. Next, I'll go over Bolt optimizations in brief, and then I'll share the results of optimizing Clang. I'll conclude with a few notes about applying Bolt. What is Bolt? It stands for Binary Optimization and Layout Tool, and its main focus is to optimize the layout of the application so that the hard code is placed compactly and contiguously. It only makes sense to optimize medium to large applications suffering from high iCache and ITLB misses. Clang is a great example of a medium-sized application that has a fairly high number of iCache misses. The results here are taken from CGO 19 paper for bootstrapped Clang 7 as a baseline, that Bolt can deliver up to 52% speed up versus O3 and up to 20% on top of both PGO and LTO. More on that later. Bolt supports ELF files on x86 and AR64, and there's an experimental support for Mach-O format. Here's the usage example. The first step is to relink the application, and I need to emphasize that it's a relink only, not a whole recompilation. The option to emit relocations, it preserves identical code, only adds relocations metadata used by Bolt. The second step here is to record the LBR profile of running that Clang binary on some input. The main part is the line with LVM Bolt. What it tells is that Clang 12 as an input binary, that we use perf data that's produced by perf record, and that the output is clang12.bolt. And following lines enable optimizations, reorder blocks and reorder functions, function splitting, and the identical code folding. And the final option, dynastats, prints dynamic execution stats, how Bolt was able to optimize the binary with that profile. What's the I-count reduction, taken branch reduction, etc. And the perf stat lines are to accurately capture the runtime. One note here is that runtime of Bolt itself is on the order of a minute for Clang. By default, Bolt would skip over functions with no profile, which is typically a majority, and it uses multiple threads to parallelize optimization passes. So this slide shows the data flow, and that there are few dependencies for Bolt. As you can see, the app is run and being profiled on the PC or in the data center, and the same app is used as an input to Bolt to produce an accelerated application. Profiles can be merged from either the same PC of different workloads or from multiple computers running the same application. And that combined profile can drive better results. The approach used by Bolt is a post-link optimization. This is in contrast with PGO, where the profile is mapped back to IR, and in contrast with LTO, where the optimizations are done at link time on IR. By applying the profile-guided optimizations directly to the binary from which the profile was collected, the accuracy of the mapping is the highest. This allows handling binaries with no source available, such as third-party libraries. It is also compiler agnostic, although we only test with recent GCC and Clang. The profile that is used by Bolt can be either sampled from the hardware using Intel's LBR using Linux perf tool. LBR allows sampling the production binary with very little overhead. Alternatively, when LBR is not available, such as in VM environment, it is possible to use Bolt's instrumentation mode to instrument that input binary and collect instrumentation profile. Here's the pipeline of Bolt binary writing. Bolt uses the LLVM compiler infrastructure to handle disassembly and modification of binary files. Few things to note here. First, Bolt expects certain codegen, for instance, jump tables layout produced by GCC and Clang. Second, the optimization passes are not reused from LLVM, as Bolt's IR is different from LLVM IR and machine IR. We built Bolt IR on top of MC layer and internally call it MC+. Emit and link is using LLVM's runtime dynamic linker to resolve references between functions and local symbols. Finally, the binary is rewritten with the new contents, and ELF structures are updated to reflect new sizes. And Bolt is able to update dwarf debug information. This figure highlights what happens with the function layout. Hot functions are placed contiguously. This reduces ITLB pressure as hot code is contained in less pages. Same thing with basic blocks. This figure highlights the basic block layout optimization, where the function is split into two parts, hot blocks and cold blocks. This improves the instruction cache utilization, since the cache line with hot code wouldn't contain unused code, except for one line on the picture. I wouldn't go into much details about code layout algorithms. I'll just mention that both are state-of-the-art algorithms with significant effort invested into the design and tuning. Now, the application layout can be visualized using the heat map. The heat map shows how hot is a given block of an application's text section. The whole text section is divided into 64 by 64 grid, and hotness is given as a color coding logarithmic scale. The takeaway from this slide is that compiler cannot do layout well, as profile changes during code transformations, such as inlining, unroll, and other code duplication. Even with PGO and LTO, the application's code layout is still not compact. And as you can see, Bolt improves the compactness dramatically. Bolt's main optimization is layout, but there are several more, such as indirect branch devirtualization, identical code folding, and more. I refer you to the paper for speed-up breakdown. Now getting to the results. These results are taken from Bolt CGO 19 publication. The workload is the Clang built from scratch using Ninja Clang. The baseline is the bootstrapped Clang built with O3. The first bar is Bolt was able to achieve 36% speed up on top of that binary. The second bar is when Clang is built with instrumentation PGO and monolithic LTO, the speed up is 30%. With Bolt applied to that optimized binary, the speed up is 49% over the baseline. Bolt's training workload in both cases is GCC build. So for this experiment, there's a proper separation of train and test sets. Note that the CPU Ivy bridge is fairly old, and in general, Bolt's impact is more pronounced for older hardware with smaller caches. Likewise, the results are more pronounced for newer software with larger code size. Now, how to apply Bolt. Bolt can be applied on top of both PGO and LTO for the best performance. As I mentioned, Bolt requires relocations preserved in the binary in order to discover all code references to perform code reordering. One note about representative workload, it doesn't have to be long. 1 billion dynamically executed instructions is enough in practice, which can be collected in around 1 minute with LBR sampling. We're working on upstreaming Bolt into LLVM's monorepo, and the tentative timeline is around LLVM 14. Once Bolt is in tree, it can potentially be added to the Clang bootstrap build, perhaps as stage 3, or integrated into test release script. with that, I would like to wrap up and thank you for your attention. I invite you to try Bolt for speeding up your builds. Thanks.
Thank you so much, Amir. It's really exciting to see those kind of numbers posted, and for sure, I think something that a lot of people are really going to want to play around with now after this talk. In particular, we look forward to having you back in Linux Plumbers next week. We'll be talking about using Bolt on the kernel kind of thing. So I think one thing that would be super interesting for us to see there, kind of feedback we got from kernel developers when trying to upstream PGO support was that, it would be great to just use the perf utility to collect the profiling data. And we actually weren't doing that. We were exporting the compiler RT interfaces via sysfs node, which is kind of a mess kind of thing. So I think having any kind of numbers and maybe numbers minus PGO would be super helpful for us to revisit PGO someday kind of thing and show that, all of these things are additive and, all these things together just add more goodness overall kind of thing. So anyways, fantastic, awesome work. Thank you so much. And up next, we're going to have Martin is going to describe for us a little bit some issues with packaging LLVM Min-GW. So Martin, if you're ready to go, it's all yours.
All right, thank you. So LLVM Min-GW is free toolchain targeting Windows for all four current architectures. So when people talk about Min-GW, they usually refer to the whole toolchain consisting of both GCC, bin-utils, libgcc, libstandard C++, and the Min-GW SDK for the headers and import libraries and everything. And there's a number of different pre-existing Min-GW toolchains, both available out of the box in Linux distributions as cross-compiler packages and also as standalone packages on Windows, and also the MSys2 package manager with both the toolchains and lots of pre-built packages. So the background for why I'm working on these things is that originally there was no free toolchain targeting Windows on ARM, and some open source projects prefer not to use MSVC, both for philosophical and practical reasons. And GCC doesn't still have support for Windows on ARM, but LLVM happened to have a fairly complete support for Windows on ARM, and also happened to support targeting Min-GW setups. So if you're targeting x86, it's pretty easy to just swap in Clang instead of GCC in an existing toolchain and use that. But when you're targeting something that isn't supported by GCC and bin-utils at all, you need to bootstrap the whole toolchain from scratch using only the LLVM tools that support this architecture. So I picked up an effort started by Martel Malone, where the main missing pieces that he was working on was getting support for LLD, the linker, and LLVM DLL tool for creating import libraries from symbol listings. These got merged upstream in 2007. And then with those in place, you could maybe, in theory, use libgcc and libstandard C++ from GCC, but it's kind of unclear how you actually build them standalone from the rest of the GCC. So we went for building everything from scratch with the LLVM counterparts, compiler RT, libanwind, libc++, and so on. And then during the same time in 2017, there was lots of rumors about Windows 10 desktop coming on for ARM64. And since Windows 10 on ARM64 wasn't out anywhere, there was a couple of just standalone exe files in the Windows SDK. And Wine had got some initial support for actually running these exe files on Linux. But the most trivial binaries worked. Some of the more complex ones didn't work because Wine needed to emulate the Windows version of variable arguments, which needs compiler support. So I set out to add support for that in Clang so that I could use Linux Clang to build Wine to emulate ARM64 Windows, which doesn't exist, but at least run the couple exe files that do exist out there. So with that in place, another person also started on adding the initial support for ARM64 targeting in LLVM, which I also picked up and got this kind of working. And since the actual OS itself, Windows on ARM64 desktop, didn't actually exist at this time publicly, I had the reference environment where I was running the binaries that I built in Wine on Linux and developing the compiler and linker to make something that I can at least test in the emulated fictional environment. And most of this was developed before even MSVC was out targeting this system. And at the point when I got access to a prototype device, my toolchain was pretty much working already, and only had to fix 2 small remaining bugs to get actual code running on the new OS and new architecture. And this when the whole Windows 10 on ARM64 ecosystem was launched at the Build conference in 2018, they actually demoed VLC built with this toolchain as one of the showcase applications. Although the presentation told the entirely opposite story. The presentation said that this was built with MSVC and changed 0 lines of code and so on, which wasn't actually true at all. But they wanted to tell their story, and we had actually built in an entirely new toolchain because it's easier to build a new toolchain and fit that into AutoTools than getting AutoTools working with MSVC. So the LLVM toolchain, LLVM Min-GW toolchain, consists of entirely unpatched build of LLVM. Part of the idea has been to make it usable with any Clang LLD binaries from any distribution, although I, in practice, build them as part of this as well. Then, on top of the LLVM build itself, because it has got 4 different sysroots for the 4 different supported architectures. They share one include directory, but keep individual directories for all the libraries. And then it also has all the runtimes, compiler RT, built-ins, lib/wine, libc, C++, and sanitizer built for all the 4 architectures. And then on top of these components, it's still got the usual earlier mentioned wrappers that everybody have. So it presents them as the regular GCC style cross-compilation toolchains, both with Clang suffixes, but also GCC. So if you type any triple and -GCC, it still executes Clang to make sure that any build system that expects these work as they used to. So those wrapper scripts just invoke Clang with the requested target triple, and also a couple more options for setting the defaults. The wrappers are shell script to make them easily hackable, but on Windows they are actually native executables. And since I'm forcing a lot of different default options that aren't relevant all the time, Clang can warn about these, so I unfortunately have to add the options for silencing the unused arguments. You could do this differently. You could build Clang with hard-coded defaults to make a default compiler RT, libc++, and so on. But in that case, when I'm building a cross-compiler, the Clang executable itself wouldn't be usable for anything when building things for the host system, since I'm not building any other runtimes for the host system. And I could also use the Clang configuration files, which have existed a couple of years, but I looked into that at some point, and it might be possible, but I haven't really tried lately. So then for some fun hacks that I had to do while setting this up during the years. So originally, LLVM object copy didn't support the Conf object file format. So there was no working strip tool. And for Min-GW targets, you usually get all the debug info embedded. So you want to strip the build outputs. And you could use GNU object copy, but it doesn't support the ARM targets. But since the stripping operation doesn't really need to understand the architectural content of the files, I made another wrapper for this that just modifies the header files, pretending that the binaries are x86, invoking the GNU tool, and then restoring the header fields afterwards. And that used to work pretty well, but it's, of course, kind of ugly. And you don't want to need to build bin utils just for this one single tool. So these days, the toolchain generally work as cross-compilers. You can run them on basically anything, on Unix and also on Windows, and all the toolchains, both from Unix and Windows, can cross-compile to all 4 Windows architectures. And of course, it does work on Mac OS too, but I haven't made any binary releases for that. And I build the toolchain by every time bootstrapping from scratch, having no files for the intended target, building LLVM using the host compiler, which is usually Linux, then installing the Min-GW headers and building the base libraries, import libraries, then building compiler RT on top of that, and that makes a usable C compiler toolchain, then building lib-unwind, libc++ on top of that, which makes a usable C++ compiler toolchain. And then after that, for building a toolchain that does run on Windows, using the toolchain built in the previous steps, I cross-compile LLVM using this, and then that gives me a setup of LLVM which I can run on the target system, but I can't run it natively, so I don't rebuild the sysroots, I don't rebuild the runtimes, I just copy them from the cross-compiler toolchain. And I originally started my toolchain trying to, as a playground and my own reference testing environment for how to assemble these things, but there's been some uptake in other systems as well. So for example, the MSys2 package manager have got a separate package repo and environment where everything is built using Clang instead and using libc++ and so on. And they currently have built, well, around 90% of their packages using this toolchain. Then for the distribution side of things, how am I testing this? So this is done as an entirely volunteer effort with essentially no resources at all. So I'm testing it with a nightly build on Linux, where I build the latest version of both LLVM and Min-GW W64. And since if you're ever building an unproven version of LLVM, you need to build it with assertions enabled, because otherwise you won't know when things go astray, and you'll have very fun bugs to hunt. After building the new toolchain, run a small set of smoke tests to validate that the toolchain seems to be working. And if it works, I install it as the latest nightly build. I run these tests, I build this in Linux, and run the tests in Wine on x86. And I have a dev board running on ARM connected over the local network and run the ARM versions of the tests there. I keep a 1-week window of the older nightly toolchains. So if there's some regression in any aspect of the toolchain, I have a couple of older versions that I can cross-check against to see where it actually regressed. And then later on in the nightly build, build a set of open source projects of interest to see if anything goes wrong. So in most cases, if there's bugs in LLVM, this trigger asserts, and you know for sure that something, you pinpoint exactly where anything is wrong. Some projects are just do build testing to find if anything goes wrong during the build. And for some projects, I build and run their tests as well. But since I only run this on Linux, I can only run such tests that work in Wine. So they won't catch if any project is doing anything API-wise wrong, especially when it comes to subtle details in Windows. But if the compilation of a project worked last week and doesn't work this week, then you will notice these details at least. For the small and important things, I test all combinations every night. So, for example, for FFmpeg, I build and run all tests for all 4 architectures every night. And these usually catch quite a few of misoptimizations. And for heavier, bigger things like building all of VLC, I just build for 1 architecture per night. So after 4 days, I have tested the latest version on all 4 architectures. Kinda. You won't find all regressions immediately, but you at least get a decent test coverage with next to no resources at all. And the sooner you find a regression, the easier it is to handle when you can ping the people who caused the regression. And also, as everybody involved knows, that building LLVM takes a lot of time. So if you end up needing to bisect, it will take a really, really long time. So to ease this aspect, I run a background job on the same machine that runs that continuously runs and fetches the latest version of LLVM, the toolchain, and builds it and populates a C cache. So if you need to bisect and build any version of LLVM during the last couple of days or so, it goes usually much faster if it happens to have been a version that has been built before and is cached. So as long as I catch regressions within a couple of days, it's pretty easy to bisect them. And like everybody else are saying as well, when you're testing and living at head, you know that you can release at any time. And the upcoming release branches aren't that big surprise as they sometimes are. So earlier I used to do releases from any random git snapshot of LLVM, but after things have matured a bit and things have slowed down, I've settled down on doing releases based on the LLVM stable releases only. And there you can have a bit more confidence that this is actually tested by somebody else than me as well. So that was everything I had to say about this. And I take questions in the GitHub repo for the conference.
Awesome. Thank you so much. This was such a detailed talk. There's so much awesome information packed in here. I'm definitely going to go through the slides afterwards with a fine-tooth comb. You know, I find myself having even discussions with my own team and teammates about even like your slide about building LLVM to change the implicit default compiler runtime and linker and C++ library kind of thing. And you know, there's the thing that would be interesting for me to play with, I think, is almost like what if some of those flags were opt out instead of opt in for LLVM? Would be kind of interesting. Yeah. How does that affect different builds?
Yeah, it's kind of a well, since Clang has these different personalities, you can use it just as a single drop-in, where you drop in Clang instead of GCC in the existing GCC ecosystem in a Linux distribution, or you can have the whole distribution of all the LLVM tools, and then you have to build all the runtimes as well. And you know, you can do it both ways.
Right. So today we have a great demonstration actually of kind of both of those. Right. Is we have some distributions that are very or platforms that are very heavily you know, that are easy to switch over and some that aren't, kind of thing. So I think that's a very interesting demonstration of some of the challenges that we face and that LLVM is able to tackle mostly effectively. It's mostly just kind of sharp corners for some of these combinations and stuff. So thank you again so much for your time. I really appreciate it. And we're going to have John do part 3 of his next talk at the very end. So Tom will be doing his talk from 1:55 to 2:10, and then we'll have John kind of finish up the conference there, kind of thing. So now we'll take a 30-minute lunch break, and hopefully we'll see everyone again when we get back from that. So that break will end at 1:10, and then my teammates Parama and Steven are gonna present about Android's AOSP LLVM distribution. So make sure to stop by after lunch for that, and we'll see you soon. Thanks, everyone. Welcome back, folks. Welcome back. We'll give folks another minute to hopefully finish up their lunch if they're here on the West Coast with us. Thanks, everyone, for being accommodating, folks worldwide, since maybe you didn't need such a long break, but just going to give it one more minute and then we'll get started. Okay, welcome back, everyone. Thanks for attending the LLVM Distributors Conference today. This is our final block of talks for the day. And starting us off is going to be my colleagues, Parama and Steven. It turns out Steven's actually my boss. Please don't fire me, boss. I promise I'll write better code one day. Anyways, if you guys like to take over presenting, they're going to tell us a little bit more about how we package and distribute LLVM for building Android.
All right, everybody, let me just switch this over to present. Hopefully that is
cool. Looks good.
All right. So yeah, thanks for having us and organizing this, Nick. I've been enjoying it so far, and I hope that our presentation is similarly entertaining and helps continue this group therapy session for many of us who've been doing this for quite a long time at this point. So this is the talk about what we do over in Android, or sometimes you'll hear us refer to it as AOSP, which is the Android open source project. We sort of set down this path. I've been working on LLVM and Android for over 11 years at this point, previously not just on like C and C++ compilation of Android, but from some prior projects. And then as we eventually came to realize like we should be heading towards a Clang LLVM world, that became more of my core job. And these days there's quite a team put together that tries to get this into shape for our uses. So we're basically the team that does maintain what we call the Android toolchain. It's still a fairly small team relatively for how many different kinds of users that we do actually have. We chase top of tree LLVM, similar to a lot of other folks in and around Google. There's not a lot of people looking at the stable releases because they really want to have some of the newest features. In particular for us, we're in this next part, I'm talking about bringing all the LLVM goodies to Android. We've done some work, even more recently, collaborations with the Dynamic Tools team in the other parts of Google to bring things like MTE, which is the memory tagging extension for ARM. So supporting that could not wait for a stable release. There were, many other pieces needed there, and so we wanted to deliver that and have that working for our own testing purposes, so we could actually get more of that work bootstrapped. So we bring a lot of these other LLVM features to Android. So obviously PGO and auto FDO. So this is not even just in the normal sense of what we were just talking about for PGOing Clang itself, but we also do support PGO and auto FDO for Android builds and Android developers. So we have instrumentation builds for doing PGO of a handful of components that are performance sensitive, that we have good benchmarks and sort of like micro benchmarks and workloads that are sufficient for creating the profiling data there, and we get some nice speed ups out of that. And with Android S, that's shipping real soon now. We actually have auto FDO based on profiles from our Droid fooders, which primarily consisted of most of our team and some other folks in the Android, dog fooding programs collecting data automatically from the device and using that to optimize what else is going on. So we brought that there. We also do use Clang Tidy and the static analyzer. This is work that we do to sort of keep our builds reasonably healthy. Other folks contribute by watching for increases in those kinds of warnings or diagnostics that are generated there, so that we can patch those and get them addressed by various other folks. And Android remains relatively clean. Although we don't fix all of the tidy warnings that we find, or static analyzer. And then we also have code coverage, which is something that my colleague who is presenting the next half of this, has been a huge part of implementing Android support for this. So having code coverage for our entire platform, cross-process, system-wide coverage, so that we can ensure that our tests are providing good value to us, and that we know that the quality of our entire distribution is high. Clang built Linux is another core part of what we do. Nick is the lead on Clang built Linux. Don't let him tell you otherwise. And Android's toolchain and Android like AOSP project is the first and largest shipping user of this. So we have Clang built Linux on our phones for 4 years at this point. It was 4 years ago that we did our presentation at the LLVM developer meeting about this, and that was where we sort of announced that yes, like we have an entire phone that's all Clang built code. So yeah, so we're doing this for all the native code in the Android platform since about 2017, including the Clang tools used during the build. As I said, the kernel is Clang built Linux. We have another couple of components that also deal with this. Bootloader, CHRE is this thing, Context Hub runtime environment, and this is basically for managing sensors and other things that we want to run at like sort of lower power modes and that don't need to interrupt the main processor or main cores on the device to feed information around. So that uses our LLVM toolchain. We also have a whole slew of native app developers, both first-party and third-party, via Android Studio and the NDK, which you may have heard of. And so the NDK actually does ship our Android toolchain as well, and that is a predominantly games and application programmers who want to write cross-platform code in a high-performance way. So they're of course using C++, and they then demand a high-quality C++ toolchain. And we made the switch over from GCC to Clang a little bit after we did it for all of our platform stuff, but we have been firmly in the LLVM camp for a while there too. We also have some tools like the emulator, the Android SDK, all of those tools that are like ADB, AAPT2, which are like packaging tools, and other things for building actual like regular Android applications out of Java or Kotlin. Those all also use our toolchain to build their sources and produce those host tools that people use. Also OpenJDK. And we have to do this across a wide variety of platforms like Linux, Mac OS, and Windows, which of course delights everybody. We recently had to have been adding support for universal binaries on Mac OS, and on Windows, we use Min-GW as well. So it's fantastic that LLVM continues to remain pretty great in working with that community too. And then this is the last slide that I'm presenting. So project-wise, we build LLVM, Clang, and LLD, libc++ ABI, libc++, and compiler RT. So we're firmly in all of the runtimes these days. Clang Tools Extra is where we get our Clang Tidy and LLDB. We also ship OpenMP and Poly in the NDK. We don't particularly use OpenMP or Poly necessarily in Android platform yet. But there's no reason that to really stop us. Just that we don't have a lot of code or users that are necessarily doing something with that. We also require a lot of stuff to be cross-compiled for the device. We have a large number of and variety of these targets: ARM 32 and 64, x86 32 and 64, because we do a lot of cloud testing and emulator testing of things. So x86 tends to be quite important to our testing story. But also the ARM side of this, since that's where the vast majority of devices are these days. So with that, I'm going to pass it over to Parama to talk about the rest of this.
Yes. Hi, everyone. Hi, my name is Parama. I work with Steve and Nick in Android's Toolchain team. So I'm going to give you all a bit more detail on how we build and release our toolchain. So our toolchain build, unfortunately, is not pure top of tree. We need like a few downstream changes, 6 of them, to make them work with the Android code base. 2 of them are very gnarly. Like one of them is with where our like Android build rules doesn't play well with LLV, and the other is when some recent changes with how Clang handles built-ins that breaks like our use of 45. So yeah, besides that, like this used to be a bigger list, and we have been trying to like whittle it down, and it's 6 right now, and hopefully it goes down in the future too. And so we build upstream LLVM project with these changes, and we use like a Python-based like build script, which I have linked in the slides, and which basically just invokes CMake multiple times to build a 2-stage Clang, and then, for example, to build the cross-compile Windows toolchain, and also cross-compile the runtimes needed for the Android device itself. So we build, like Steve mentioned earlier, we build compiler RT, OpenMP, Poly, and so for and all of those using multiple CMake invocations. And recently, we have also started shipping like LLDB server for Android, which we replaced, which replaces GDB. So, and then there is like a slew of more tools that we now build along with it. For example, like Swig and libedit and libn curses, etc., which we all build with Bootstrap with Clang nowadays. So we also use PGO and ThinLTO to speed up our build times, and like George mentioned earlier, we in the earlier presentation we use a mix of ARM and x86 code and C and C++ code to get a fair amount of mix. We wish we could build all of Android with it, but we didn't really see much motivation to like spend the extra build time collecting these profiles. Can you move to the next slide, please? Yeah. So as our release process is, we are releasing a new toolchain every like 4 to 6 weeks, and it's slowly getting shorter and shorter. So we are getting closer and closer to top of tree right now. We work with the Chrome OS toolchain team, and we collaborate with them a lot in terms of like which revision we pick, and then we work on like finding all the issues with the Android and the Chrome OS code bases, and then also like if we need to cherry pick fixes from upstream, like we share it with that team. So the team also maintains like very good utility that kind of tracks reverts on upstream. So if we give it like a base revision, and it'll find all the reverts, all these changes that were reverted from that particular base. So we use that to beat out like bad changes before we actually find that in production. So yeah, so like I said earlier, we have like a 4 to 6 week release cycle, but that does not mean like our releases are like the support window stops at 6 weeks, because we also cater to the Windows. We also cater to the NDK users where the support window is close to a year. So we also end up having to like find issues and rediscover issues that are reported by the NDK users, and then fix them later. So can you go to thanks, Steve. And so we also have a separate testing branch that currently is at the same cadence of like 4 to 6 weeks, which we really like to start testing like nightly with upstream. And one of the problems with this testing branch, like that was also mentioned earlier in the earlier talk was that like with the build systems using like wall and werror, this kind of like keeps breaking the build anytime like Clang's warnings get like stricter or like new warnings get added to wall, and then so we have to be have some mechanism to handle this use case. And how we handle this is that we have like a wrapper for Clang and Clang tidy, which kind of run like a command with run a build command with a new Clang, and if it breaks, it reports the errors for bookkeeping, and then also like reruns the same command with no error. And if we are able to make progress with that, that's good. So we can continue testing the new revision of Clang. And then we also have like separate like scripting and testing infra to collect these logs, so we know what we're getting into when we are actually updating a release, when you're actually doing a release. Yeah, so that's kind of like a sliver of what we do. So there's like far more details that we skipped here, and you can kind of find all the other things we are building from the build scripts that I linked in slide 5, or we can also like continue the discussion in the GitHub topic, GitHub issue. All right, thanks everyone.
Great, thanks so much, guys. Have to be honest though, I didn't learn anything new from this presentation. Just kidding, we're on the same team. I know all this stuff, right?
You better not have learned anything new from this presentation.
What? Right, yeah. Right on, thanks so much, guys. So up next is gonna be a familiar face. We saw him earlier today. Another colleague as well from Google. Peter is gonna put on his Fuchsia Toolchain team hat. I think he even changed his shirt just for this talk. Look at that. Wow, nice.
Yeah,
okay.
Just to spice things up.
Yeah, I almost didn't recognize you there for a second. Okay, cool. Thanks, Peter. All yours.
Okay, thank you. So hello again. In case you haven't seen my previous talk, I'm Peter. I am the lead of the Fuchsia Toolchain team, and in this talk, I'm actually gonna talk about our toolchain. Now, I should start by saying that I believe that a lot of what you're going to see, what you're going to hear, is going to sound very familiar. I've actually, when I was watching all of these talks so far throughout the day, I've certainly seen a lot of things that we do as well, and we are definitely standing on the shoulders of giants, and like we're like learning a lot from other teams at Google, like Android, Chrome, Google Free, but also like other non-Google teams. So you know what you're going to see should be familiar, but hopefully you might also learn a new thing or two. So first, let me start off by telling a little bit about Fuchsia, because you may have heard the name, but you may not be familiar. So Fuchsia is a new operating system that was developed by Google. It has been in development for the last 5 years, and just a couple of months ago, we've announced like our first release. We've shipped this new system on a first set of products, which is the Google Nest Hub smart displays, like the one you can actually see here on the slide. To build all of them, an important component is the Fuchsia Clang toolchain, which is a complete C and C++ toolchain distribution that is built entirely on top of LLVM tools and LLVM runtime libraries. And we use it really for everything. We use it to build all of Fuchsia. We use it to build bootloader and kernel, all the system libraries, user application, and even our host tools that we use for other development. And I think this is one of the places where we really take a lot of advantage from a lot of features and the cross-platform support that Clang has. So for example, we use it to build a bootloader, which is a UEFI application. And because Clang has native support for building P binaries, and then there is LLD link, we don't have to mix and use different tools. We can just just take LLVM and use it for everything. This toolchain is also being used by some of other related projects that we work closely with, like PGO'd, which is the different system that's intended for sort of more embedded uses. There's Dart and also Flutter, which we use heavily throughout Fuchsia. Within Google, it is being used by hundreds of developers. We also know about some developers outside of Google who started using it as well. And we also use it on our automated infrastructure. So that's thousands of builders, similar to Chromium. Our goal, and this has been our goal from the very beginning, was to deliver a modern cross-compiling LLVM-based toolchain. Like we tried to avoid any legacy components, and from very early days, like we've been using and shipping like pure LLVM toolchain that was only based or built from LLVM pieces. One of our goals and why we've really decided to go all in on LLVM is to provide the same exact experience across every supported host platform. So it shouldn't really matter whether you are building on Mac, on Linux, or on Windows. You should get that same exact experience. And just like Fuchsia, even our toolchain is open source. Everything we use, everything we do is open source, and anybody should be able to reproduce our toolchain build, and even our infrastructure if you want to. The philosophy is similar to many other projects at Google. Like we live ahead. We try to release as often as possible. Our goal is to release on a weekly cadence. Sometimes we may slip a little bit if there are some upstream breakages. We don't carry any downstream patches, just like Chromium. Like our preference is to instead develop any new features directly upstream and just adopt them as soon as possible. And that also means that just like Chromium, we are the ones that always come into your changes and complain when things don't build. And we really appreciate all your help and collaboration. Our toolchain is completely self-contained in terms of its host and target runtime requirements. The only thing we really depend on is the system library, like your C library. Other than that, it's completely hermetic, and so it can run on a variety of different versions of operating systems, different Linux distributions, what have you. And speaking about the range of platforms and versions, we do support Linux, macOS, and Windows as a host platform. We support x86 across all of these. For ARM64, officially we only have Linux ARM support right now, but we're also actively working on support for macOS on ARM64, and the same for Windows. This should hopefully be coming soon. As for target platforms, it's the same combination with addition of Fuchsia, which is really the target that we care about the most. As for toolchain components, like I said, it's a pure vanilla LLVM toolchain. We use Clang, we use LLVM during assembler, we use LLD as a linker. We actually configure these to be defaults directly in our CMake build, because that's what we want everybody who's using our toolchain to use to get that same experience everywhere. We also include a bunch of other tools like Clang tidy, Clang format, ClangD, lots of other utilities that we find useful. And as for runtimes, we use compile-RT for built-ins and for all the other runtimes like sanitizers, profile, and so on. We use libunwine, libc++ AVI, and libc++ Silicon. So like I said, is a pure LLVM toolchain. The way we build this is, just like I described in my earlier talk, we use the LLVM runtimes build. In fact, one of the reasons why we got so invested and why we've been working a lot on improving runtimes build over the years is our toolchain. And we try to lead by example. So we try and build everything with a single CMake implementation. We also rely on the multilib support that I described, and we actually include a number of multilibs for no exceptions. We have sanitized versions of runtimes like libc++, which we find really valuable in our development. For the production toolchain, we use two-stage build. The second stage, we always optimize with LTO. We're also working on PGO. We're not quite there, close. we kind of ran into what George hinted at, which is sort of this like analysis paralysis, where we spent a lot of time just trying to figure out what is the right corpus. But I think we finally figured it out, and this should be coming in very soon as well. When I said we're building with a single CMake invocation, this is really what we're aiming for. Like our hope is that you should be able to build a full toolchain just by passing a toolchain file, which configures the host compiler and a few other bits, and a path to Fuchsia SDK, and then you point to the Fuchsia cache file, which is part of the LLVM source tree, and off you go. And out that comes a full toolchain. We're not quite there yet. I've actually omitted some aspects from this invocation, and I'm actually going to get into some of those a little bit later. As for testing, we run tests for all the tools that we include in our build. We also run tests for all the runtimes, but only on host. We don't yet have a way to run tests on Fuchsia, but this is something that we're also now actively looking into, and I will touch on that a little bit later as well. Because testing is really important, we have also extended lit to support a new output format, which better integrates into our infrastructure. I mean, this is shown here. So when we see a test failure when running one of the LLVM test suites, traditionally you would have to open up the SD out and then just go through this log, which is thousands of entries, and figure out what is going on. Instead, in our case, you immediately see like what test failed, and then you can switch to second tab, and there you see just the results for the failing test. We found that in our experience, this really helps when you have to keep on monitoring folders, triage new issues, and so this was really valuable. As for distribution, we use the LLVM build distribution support. That's part of the upstream CMake build to control what goes into our toolchain and not. All the cache files that we use are in LLVM source tree, so you can check them out. You can use them as a starting point or source of inspiration. And our toolchain build is like I said, completely self-contained. We link everything statically except for the systems to runtime. And it's going to be sometimes challenging. I wish it was easier, and we are looking for ways to improve that, although we haven't really come up with a silver bullet. But we find that this is really valuable when we want to support a wide range of distributions, wide range of like different versions of systems that your toolchain may be used on, as is the case for us. As for automation, like we rely extensively on automation. I think that's really the only way to make it feasible to live ahead and roll as frequently as we are aiming for. We continue to build our toolchain, and anytime we successfully build a toolchain, we use it to build and test the full system. Every toolchain that we produce, we upload to our package distribution system, so it's immediately available for use. So we also package it into a Docker container, which is then used, pushed into our distributed compilation service, called Goma, which some of you may be familiar with. As for our infrastructure, we use Lucy, which is the CI system that was developed originally by Chrome, but it is now used by many other teams at Google, which is also open source. And we use a combination of both physical machines and virtual machines for both building and testing. I mean, the physical machines are really important for targets like ARM64, where there isn't really good offerings, from various cloud providers. We're also trying to minimize the amount of unnecessary work we have to do by using stage builds. So, we start off, we try to do, sort of quick smoke tests, like build as quickly as possible, figure out if the revision or change the lighting upstream is usable, and if so, it's only then when we trigger a full production build with all the optimizations enabled. We're also trying to simplify the triage process by automatically collecting any crash reproducers. Right now, we support Clang reproducers. We would also like to get LLD eventually, something that we're working on. Going forward, we would also like to look at other ways to improve this by maybe supporting automated bisection and bug filing. I mean, this is what it looks like in practice. And here you can see commits going chronologically from bottom to top. So on the left-hand side, the first 4 columns, those are the fast CI, what we call CI builders. These build just single stage, no aggressive optimizations, no LTO, PGO, or anything like that. Really, the goal is to build as quickly as possible to minimize the amount of unnecessary work. If that build succeeds, it triggers the second stage of builders, which we call prod, which is the second, like the next 4 columns, and those are the ones that use, LTO, the future will be PGO, and really try to produce the production toolchain that we're going to later use. If that succeeds, we then trigger the canary builders that try and test out this just built toolchain together, with the Fuchsia and see if everything works when we do full system build. And it also triggers the production of these Docker containers that I mentioned. This is what it looks like when we encounter a crash on one of our canaries. We automatically pick it up, we package it, and we push it into cloud storage so that whoever is monitoring these builders can quickly pick up these reproducers and upload them straight to Bugzilla or just try and use them locally. And again, this is really helpful in staying on top of all these changes that are coming in. As for areas for improvement, like one of them is better support for building LLVM runtimes as universal libraries. There's already some support for building universal libraries for compiler RT, but what is absent currently is built-in support for building things like libc++ libraries. We work around it by using various additional scripts, but it's really not pretty. I would really like for this to be supported directly in a CMake build, and it's something I'm looking at improving. Another thing, like early on, I mentioned on this slide that our goal is to just run CMake and then run Ninja, don't do anything else. The reason why that's not the case today is because we want to keep our toolchain self-contained and hermetic, so we also have to build other dependencies like zlib, libxml, and then point CMake at those locations where those libraries will build and install. I think it would be much nicer if we can avoid all that additional logic by supporting the building of those dependencies directly from the LLVM CMake build. And finally, one of the limitations that we are sometimes running into is that having like a full tool chain, especially statical link one, means that the toolchain can be quite big. Our toolchain is roughly 400 megabytes compressed, 1.4 gigabytes uncompressed, and for developers that are on their home connection, which is true now during the pandemic, it can be problematic, especially if you keep pushing new toolchains once a week or even more often. So we've been looking at ways to reuse the size of those toolchains, and one of the promising paths that we're exploring is to have a support for combining different tools into a single binary in what we call BusyBox style. You may have seen some discussion on this on the LLVM dev a couple of months ago. As for requests from the community, I think the two big ones, we would like to see efficient support for cross-platform testing in lit. This is going to be really important when we start running tests on Fuchsia, because we cannot really do full build on Fuchsia. That's probably still some time out. So we need a way to compile tests on host and then run them on a target. There's some rudimentary support for doing that in runtimes like libc++, but it's very inefficient, and we would really like to see this become more of a first-class feature that's supported across all of LLVM, across all the runtimes. Another feature request would be a better way to report downstream test results to upstream. Like, as you've seen, we have a lot of infrastructure. We have lots of lots of machines. I think it'll be infeasible for us to cover all of those configuration in upstream, like replicate all that with Bullbot. But we would be very eager if there was a way through maybe some kind of API to report anytime we see a failing test. So upstream gets the signal about what is going on. And we could, and ideally we would be doing that in an automated fashion rather than us going onto every change in Fabricator and just commenting that, hey, yeah, you broke us, could you please revert it? So that's a quick overview of our toolchain. Thank you very much for following through. Same as before, if you have any questions, please post them onto the issue corresponding to this talk. And like I also mentioned before, like we are looking for more engineers to join us to help make our toolchain better. So if this is something you're interested in, please reach out. Thank you.
Awesome. Thanks again, Peter. Another great talk. Next up, we have Siva Kumar is joining us from Qualcomm to talk a little bit about the Snapdragon LLVM release. Siva, are you ready to go? Are you able to present your slides at the bottom? There should be a little rectangular icon with the arrow pointing up that says present now. Worst case, we might be able to shuffle you with Tom, who's up next. Let's just see if there's any feedback here. If not, can you try to message us on one of either the Discord or the IRC channel here if you're having technical difficulties, or even maybe the GitHub issue tracker. Hey, Tom, are you available? Would you be able to fill in real quick and we could just swap maybe those last two talks here?
Yep, I'm all ready to go.
Awesome. Okay, do you want to present your screen and then we'll just flip the order there?
Sure.
And Tom's joining us from Red Hat, where he's going to talk a little bit more about Fedora and RHEL's distribution of LLVM. Thanks, Tom.
All right, how's this look? Does it look okay?
Looks great.
Okay, perfect. All right, great, thank you. So yeah, my name is Tom Stellard. So I'm one of the maintainers of the LLVM packages for Fedora Linux, and also Red Hat Enterprise Linux, which we sometimes call RHEL for short. So today I'm going to talk about how we package LLVM for these operating systems. All right, so first of all, Fedora Linux is the upstream community distro of RHEL. So Fedora has a new release every 6 months, and it's where we first package new versions of LLVM when they become available. And in Fedora, we support many different architectures, x86, 64, 32-bit x86, PowerPC 64 little endian, System-Z, ARM64, and even ARM32. And we do all native builds on these architectures, so we don't allow doing any kind of cross compiles at all. And as far as the LLVM packages we ship, so we ship 14 LLVM sub-packages and related projects that you can see here in the slide. And since LLVM is on a 6-month release cycle, just like Fedora, so we try to ship a new major version of LLVM in each Fedora release. And so as I mentioned before, Fedora is kind of the upstream distro for RHEL. So typically what we do is once we have all the packages built for Fedora and we're kind of happy with the result, then we take the same sources and rebuild everything for RHEL. So a little bit more about RHEL. So just like Fedora, we have a 6-month release cycle. So we also try to package a new version of LLVM every time there's a new RHEL minor release. We do some things a little bit differently though. For example, we support less architectures. So no 32-bit ARM and also no 32-bit x86. Although we do provide 32-bit multi-lib packages that you can use on a 64-bit host. And then as far as the LLVM sub-projects we package, so we just package 7 of them in RHEL. And the reason we do this, the reason we package less in RHEL than Fedora is because sort of our decision-making process there is driven more by customer requirements. So we try to limit what we ship to things that customers want and are interested in, and also what we can reliably maintain as a team. And I think one other thing I'll note here is we don't ship libc++ in RHEL. So for our toolchains in both RHEL and Fedora, we use libstandard C++ as a C++ library. And even though you can install libc++ in Fedora, we don't really recommend doing this because all the system libraries use libstandard C++. And it's very easy to run into problems if you try to use both or you have both of them loaded into the same process. So we try to steer people towards our default, which is libstandard C++. All right, so now I'm going to talk a little bit about how we, the mechanics of actually building the packages. And I'll go over a little bit of terminology that I use just for anyone who's not really familiar with Fedora or packaging. So RPM. So an RPM is a binary package format that's used by Fedora, RHEL, and some other distributions as well. So if you're familiar with Debian or Ubuntu, this is equivalent to like a .deb or a Debian package format that those distributions use. DNF is the program we use in Fedora and also RHEL for package management. So again, if you're familiar with Debian or Ubuntu, this is the equivalent of apt-get there. And then finally, a DNF repo is just a place where DNF fetches its packages from, usually a web server somewhere on the internet. And so for the rest of the talk, I'm going to be using Fedora as an example as I explain kind of the mechanics of some of the things that we do. What we do for RHEL is pretty similar. I've already highlighted some of the differences, but I think that the process is more or less interchangeable. So I'm just going to focus on Fedora since we have a limited amount of time. So in Fedora, our process for building packages starts with a spec file. So what a spec file does is it kind of describes how to build the packages with a mixture of this RPM macro language and also shell scripts. So I have just a small snippet of the LLVM spec file here. And you can see at the top, we have some RPM macros to tweak some of the build flags depending on the architecture we're building for. And then below, just some bash to run CMake. And then the rest of the spec file has bash code for actually doing the builds, installing, and just a couple other sort of packaging cleanups that we do after the install. So once we have our spec file is ready to go, and we're happy with it, maybe we've tested it, we package it up with the sources, and we submit it over to our build server, which is called Koji. So what the build server does is it takes the spec file, which again is just basically like a super bash script, executes it, and produces binary RPMs for the package. And then once we have those RPMs built, we have this secondary server. We call it the release server. Its name is Bodhi, B-O-D-H-I. Basically what that does is it takes the binary RPMs, make sure that all the gating tests pass, any manual tests we have pass, and then once everything looks good, it submits it for inclusion in the DNF repos so that then it's ready for users to install on their system. So that's kind of a high-level overview of kind of the process of making the packages, but now I want to talk a little bit, to get into a little bit more of the details and exactly how we build LLVM and the different sub-projects in Fedora. So I think the main thing we do differently probably than most other people is we build the LLVM packages in standalone mode. So what this means is we download one of the sub-project tarballs from the release page, we unpack it, and run CMake only in that directory. And then, the build we get from that is what we end up packaging. So it's a little bit different. I think most people probably use the monorepo build where you have all the source code together, one CMake invocation, you tell it which projects you want to enable, and then you kind of build everything together. But this is not what we do in Fedora. And so the main reason we've chosen to do the standalone build method is we want to be in a situation where it's always easy for us to push out new updates to the different packages that we support. So just as an example, let's say we wanted to apply a bug fix to LLD. All we need to do is patch the LLD sources, submit the fix, and then we can have a build ready in about 15 minutes. So it's really quick and really easy. If we were to do the alternative to this, which is to do a monorepo build where we're building all the projects together, in this case, instead of 15 minutes for the LLD fix, our builds are going to take 12 hours or more, and that's if everything goes perfectly. If we run into some other problem, like maybe there's a change in the environment that breaks one of the other LLVM packages, like, for example, a new version of glibc has been pushed to the build root, now compiler RT won't build. So if we end up in a situation like that, then now our LLD fix is blocked by a bug in another package, and this can kind of cascade and result in major delays in getting updates and fixes out the door. And being able to reliably fix bugs in sort of a well-defined, predictable period of time is very important to us, especially in RHEL. So this is kind of the main reason that we've chosen this packaging strategy in Fedora and RHEL. So another advantage of packaging this way is it just makes it easier to iterate on the packaging improvements. So whenever we're trying out a new packaging feature, it can be easy to make a mistake, or maybe we decide we want to change our approach. So it's much easier getting feedback, even for some of the packages that take longer to build, like LLVM, and we can get feedback in like 4 hours. Whereas with a monorepo build, we might be looking at the next day before we can get feedback on the changes we've made. So this is another reason why we like doing these standalone builds. It also helps us to, we can parallelize some of the builds. So for example, once we have LLVM done, we can kick off builds of Clang, MLIR, LOD, and a few of the other packages all at the same time. And similarly, once Clang is done, we can build LODB and Flang at the same time too. So that kind of helps us speed up the builds a little bit. And while we do like building the packages this way, there are some downsides to doing this. So I think the main one is because of this sort of build style, we end up dynamically linking all of the Clang and LLVM tools against the various libraries. So this can lead to some performance issues in some cases. Although there's been some improvement recently, now that the upstream, the LLVM library is linked, we're using the fno semantic interposition and the b-symbolic function flags when compiling and linking. So that's helped a little bit, but we still do see some performance loss, especially during performance startup. But we're okay with this trade-off. I mean, our goals are more about stability and predictability. So we're willing to give up a little bit of a performance in order to achieve that. So another thing we do in Fedora that might be slightly different from some of the other distributors is that we build all the LLVM packages with GCC instead of Clang. And so the reason we do this is really just historical. Fedora has always had the policy of building everything with GCC as long as the package supports it. However, this is actually changing. So we were able to get a policy change in Fedora 35. So now any package is free to choose whatever compiler it wants, as long as there's a good technical reason to do so. So we do have the opportunity now to switch our builds over to Clang, and it's something that we're definitely looking into. We did want to do it a little bit earlier, but we've been blocked for a while on this really kind of nasty bug with the LLVM any class. But I think we have this resolved now, so we should be able to move forward with this. Hopefully, once we get this release behind us, we'll have a little bit more time to look into that. And then as far as the versions that we package, so we package release candidates and final releases into Fedora. We do not package like development snapshots from trunk at all, although this is something that we may start doing in the future. We've been looking into it and trying to figure out ways that we could make it work. One of the reasons we haven't done this in the past is because the unstable API in LLVM means that if we do package a new snapshot, we may have to rebuild a whole bunch of library users in Fedora. So currently in Fedora, there's about 8 packages that use either the Clang, LLVM, or LLD libraries. And this really may not sound like a lot, but the problem with rebuilding those packages is that even just one of those packages fails to build for some unrelated reason to LLVM, then our whole update gets blocked. So kind of like the LOD compiler RT example I mentioned earlier. So this situation is kind of difficult for us. We don't want to be in a position where we have to fix bugs in other packages unrelated to LLVM just to get our LLVM builds into the distribution. So this is kind of the main reason we've held off on doing the snapshot builds until now. But this problem with the library users is not specific to the snapshot builds. We also run into this anytime we upgrade to a newer major version of LLVM. So we always need to make sure we don't break these packages. And really, ideally, we could rebuild everything against the new version, but this isn't always an option because some of the packages in Fedora may not work yet with the new LLVM releases, especially since we're packaging release candidates, so we're pretty early in the release process. But one nice thing about Fedora, though, is that it tracks package dependencies at the shared object level rather than at the package level. So even though, like, if we have a shared object like liblvm 12 that would normally ship on the LLVM libs package, if we upgrade that package to version 15 and it no longer contains that older shared library, we're still able to satisfy that dependency with another package as long as it contains that same shared object. So this is what allows us to do what we call compatibility packages. So these are packages of older versions of LLVM that exist basically just to keep all the LLVM library users in Fedora working while they transition to the newest version. And so these packages are libraries only, and we install them into their own prefix, like userlib64, LLVM 12. And we typically try not to have too many compatibility packages at any one time, usually just one or two, and we try to retire them right away as soon as they aren't being used anymore, just because we don't want to have to support all kinds of older versions forever. And so what this means is that we really just have one version of the full tool chain in the distribution at any given time. We don't ship multiple versions like some of the other distributions do. And then as far as testing, so we have several CI tests that we run on the builds. We focus on integration testing, so testing how the different components of LLVM work together or how they work with other packages on the system. We also run Ninja Check as part of our RPM build process. And then our update server, Bodhi, which I mentioned before, has this karma system where users can vote on builds, so give it a +1, -1 before they make it into the DNF repos. So we do get some benefit from this manual testing as well. So future plans for us. So one of the things we're really excited about is Fedora has this really cool infrastructure project called Copper, C-O-P-R. Basically allows anyone to create their own package repositories. So it's usually used for packaging things that aren't in Fedora for one reason or another. So we started using this for rebuilding Fedora packages using Clang instead of GCC. So the goal here is for us to provide kind of like an alternative version of Fedora using Clang as a compiler instead of GCC. So we only really have the resources to build a subset of the packages, like about 1,500 in this Copper repo. And at this point, we have about pretty close to an 80% success rate of rebuilding things with Clang. I know this may sound a little low, but our build process and what we're doing is we're attempting to do these builds by reusing the spec files that are written basically for GCC. So we can inject environment variables, do a few other things, but that's about it. So a lot of the failures we run into are really more like build system configuration errors more than like bugs or problems with Clang. And we have a few of these repos right now in our Copper project, so anyone can try them out, these Clang built packages if they're interested. We're also working on setting up a Copper with daily LLVM snapshots, so basically roughly the equivalent of app.llvm.org, the equivalent of what that provides for Debian. And we're also looking into using Copper to do some upstream testing as a way to rebuild, just use Fedora packages as kind of test cases for LLVM releases and even some tip of tree testing. So that's pretty much it. So I put some links to some of the things I talked about here on this slide. If you're curious about learning more, feel free to ask a question in the GitHub issue. Thanks again for logging on today and listening to my talk.
Thanks so much, Tom. It was really cool to get a sneak peek into and understand some of the trade-offs and really, you know, a focus on having tight SLO or SLA deadlines is something that's very interesting. Kind of thing, and you know, what are some of the trade-offs involved with meeting those? So it was very cool to see, and I think Tom also meant to remind everyone is get your release blocker bugs fixed because we'd like to get the 13.1 release out, right?
That's right.
That's right. Right on. Okay, so next up is Siva Kumar is joining us from Qualcomm to teach us a little bit more about Snapdragon LLVM distribution. Siva Kumar, are you able to present? Sorry, we're getting video. I'm not getting audio though. You might have to play with the settings. There's like a vertical ... and then it pulls up settings. And then under audio, you might be able to change out your microphone real quick. Sometimes the Google Meet will default to system mic instead of a headphone. Worst case, I have a copy of the slides. I might be able to help present them, but without audio, that might be the trickiest part. Video, we could kind of even skip, right? There we go again, video now. No audio, it seems like, though. I would say if you know some form of sign language, you could try that, but this is a compiler conference. No interpreters allowed. Kidding, accessibility joke. Thanks everyone for your patience. We'd really like to get this talk in, kind of thing. So if you can bear with us just for a little bit, I think we can get this wired up and working. It looks like you're muted now in Google Meet. If you use the UI in the web page to try to unmute. I think we may also be able to have you dial in via phone. I think there is something wired up in the Google Meet calendar. You might be able to call in. If you look at the Google Calendar invite, there is a button or part of it. There is a phone number. If you can try dialing into the meeting via phone, then I could help advance the slides for you, and then that might work. John, do you mind prepping your slides? I think maybe we can swap that schedule around too. And then Siva Kumar, if you can try dialing in via phone, then we might be able to do that after John finishes off his presentation.
Sounds good to me.
Cool, thumbs up. Okay, yeah, can you take it away, John?
Yeah. Yep. You there too, Lucas?
Yeah, I'm here.
Right. Sorry, I just clicked to the wrong slide. Oh, wait, we just finished this one. Okay, the next small gotcha in the LLVM ecosystem for us is the dependencies between compiler, RT, and libc. I'm not at all convinced I even understand the situation, but it seems like libc needs built-ins, that much is clear. Sanitizers need libc, that is also clear, and there might also be various built-in fallbacks that also need libc. At least the GCC situation has this. So anyways, with just the first two, the end result is you have this cyclic dependency between all of compile-RT and libc, and that's just confusing and annoying. But we've worked around this, but it's been involved with this huge amount of complexity, all these -d flags. If this is blurry and a wall of unreadable code on your screen, that's kind of the point. It's just too much. Each of those orange yellow things is some Boolean expression conditional, so it's over the top. What we've to distill that down, the approach we've had is we do a sort of bare metal compile-RT build that requires nothing, and then we build a libc. And then if you want the sanitizers, you can build compiler-RT again, but it still doesn't seem that great. What I've thought about is maybe compiler-RT should just be split up. I have a little bit of a math argument there, but glossing over the details, it's just, I much rather deal with mini libraries than mini configuration flags because it's more modular and less of a combinatorial explosion. And with that in mind, it might be useful to compare Rust core versus STID. Now, core isn't really a compiler-RT analog when you get right down to it, but the idea that there's sort of a minimal library and you always use that even when you're doing less freestanding, more hosted things, I think it's a good one. So the first thing is I just need to understand what's going on better, but maybe there is room for improvement there. And our last little thing, this is sort of a very minor, but with this sort of the build and the hosts are relative and not absolute thing I've talked about. Sometimes there's some source level interfaces in LLVM that sort of, well, that we adopt the GNU terminology as not using the wrong terms. And that for example, there's these is target arch macros, and it's LLVM's target, but it's your package's host, which if you're not building a compiler, which granted it's the usual case, whatever, target close enough. But if you were building, let's say GCC, and you have other target macros that mean something quite different, it could be confusing because now target is being used in two different contradictory ways. This is a very minor thing. I did open my very first LLVM patch on this, and I did a bad job of explaining it then, and it was too late to change it anyways. But I just thought I would bring it up as not something really worth fixing at this point, but just sort of an example of where our perspective and things LLVM has done have diverged, even if only in a little bit in trivial ways. And then lastly, I want to talk about some things we're doing next. Or rather, Lucas could talk about packages LLVM, which has really been his project.
Yeah, so earlier this year, basically, I noticed some regressions in our default LLVM toolchain, and specifically the one we use for cross-compilation. And so that's mostly down to the combinatorial explosion John mentioned. So some stuff stopped working, which was behind some conditional, and that conditional wasn't true for most cases most people use. So we ended up with a slightly broken LLVM toolchain. And so basically packages LLVM is a way to make this more discoverable in Nixpkgs. So we have some way of re-exposing Nixpkgs, so the entire package set with all packages we have with different settings. So we have packages muscle, which uses muscle libc, packages static that uses does statically linked executables and libraries and so on. And also all cross-compilation tool chains basically have their own package set So you can at least try to build all packages or cross-compile all packages. And packages LLVM is in the same spirit. It uses the cross-compilation toolchain for LLVM, but targeted at the native architecture and kernel and so on. So this is quite similar to Exerbo, where you take the cross-compilation code path all the time, even though you can compile natively. So this is partially a separation thing, and also just a matter of we are able to reuse a lot of work already done in Nixpkgs at zero cost. And it works surprisingly well for being such a major change, which I think really shows that people have been interested in cross-compilation and ironing out some issues in packages, in Nixpkgs. So a lot of stuff just works. And I think, yeah, probably these days also a lot of upstream packages care about Clang. We still have the issues of glibc and libgcc, of course, and we also just use GCC for those always, which is a bit annoying, especially if you have to recompile your toolchain. You're also, in the worst case, sitting there and waiting for GCC, which is not nice. And you occasionally run into odd issues. I had a good example recently was Boost. So it has a bit of an odd build system. And we haven't ironed out all the issues for auto tools and so on. So that caused some problems. And specifically there, the build system didn't really take too well to cross-compilation for one, and also it assumed that CLang is always CLang. And we do something similar to the Windows toolchain, which was mentioned earlier, where we prefix our CLang and wrap it in a shell script, which, among other things, sets the target flag automatically. So this is mostly our fault for making CLang more like GCC, and it would be nice to get rid of this in the future. And yeah, as a small thing, so packages LLVM mostly leverages the power of platform configurations we have. So that's basically the slide John showed earlier with the platforms we've targeted. And so this can also be composed to a certain extent. So you can, for example, combine musclelibc and LLVM already. But the ordering, because native and cross-compilation interacts in a weird way there, is a bit important. So the other way around, it doesn't work, for example, at the moment. And this is maybe just shows the biggest challenge. There are a lot of possible combinations and ways things can interact. And we have limited build time, limited manpower to test all these things. So that's some problem. And yeah, would be nice to be able to compile a lot of stuff with LLVM in the future, like maybe your entire system configuration and the complete distribution you actually use. But we are far from that at the moment. And topics like PGO and LTO are also interesting because GCC and LLVM differ in this regard. And it'll be interesting to see if we want to go further in that direction. We have to have additional workaround to make them play well together. If we need a wrapper script like OpenMandriva, or if the upstream packages just will be able to support both with no big trouble. Yeah.
Great. Really quick. Because the LLVM situation's been so good, actually now kind of GCC is the weakest link. So I've recently started trying to just machete through and repackage GCC as we've done with LLVM, which again, Xerbo and Salim have kind of led the way here. So, you know, it seems sort of like dead weight. Why put all this effort in GCC? But once we have both compilers having these nice per component builds for all those reasons Tom mentioned, and I kind of glossed over, then our horrendous wrappers can be simplified a lot because they're sort of taking the same things component by component and wrapping them the same way. So it's going to be like the mother of all tech that Jubilees. I've been looking forward to years when we can finally do that. And then last thing, just sort of back to the fun stuff, always trying to do new platforms. So there's an old PR of mine based on Martin's work. Really would love to get that finished off and do the Min-GW and the official SDK builds. Some FreeBSD following our NetBSD. And we can build the kernel, so even trying to see if we could make a NixOS with the wrong kernel. If I ever learn how those init-RDs, init-FSs work. Redux, Aaron Jansa, college student, did a great job throwing some things together. And I think being one of the first people to boot up, sort of all built from source and do a little, but I actually forget exactly what the milestone was he did, but it was a great job. And because we have the Googlers in the room, last pre-built Android, S1341 made some great progress, but we cannot figure out how to build Bionic from source without just taking all the monorepo packaging. So please do help. And Fuchsia too. I have a soft spot for getting out of the the Unix mire and honored to better, cleaner things. So I almost feel like once we slay all the BSD and Linux, you know, dragons there, we'll have defeated Unix, and then we can move on to fun things. So yeah, overall, it's yeah, really great to hear from you all, and we're sort of a weird distro that has you know, followed and reverse engineered a lot of other packaging efforts, but not a lot of people know about us. So we'd love to, you know, sort of collaborate with our upstreams and not just, you know, be the investigators trying to figure what's going on without asking anyone any questions. Yeah, so that's all. Thanks. Yeah, thanks to Lucas too. Thanks to Nick for well, we went over and my my technical difficulties and all that. It'll be, I guess, a decent amount of work in post production.
We'll fix it in post. Don't worry about that.
Okay, yeah. Okay. Yeah.
Awesome. Thank you both so much. And I think this is a really awesome distribution that really folks should keep an eye on, because, you know, I don't think we always need to accept the hand that we're dealt. And I think, you know, Nix does an amazing job of trying to say, you know, what could things look like if they were different. And I think that's really exciting. So thank you both so much again for your talk. And, you know, I encourage folks to follow up on GitHub for the issue tracker. And let's see, for our final talk of the day, Siva Kumar, are you able to join with audio via phone?
Hey, Nick, are you able to hear me now?
Yeah, sounds great. Hey, it's working. Nice.
Perfect. The third time seems to work fine.
Yeah, always.
But please help sharing the slide. I don't have.
Oh, sure. Yeah, I've got it ready to go here.
Looks like, you know, some sort of technical difficulties going on the desktop that I have. Yeah, let's move on with your help. I'll figure it out later. Thank you for your help.
Yeah, no worries.
So, yeah, hello everybody. Thank you, Nick, for organizing this, and it's a great opportunity for me to come in and see what industry peers, what everybody is doing in terms of, you know, distribution, which basically uses LLVM toolchain as their base, right? So that's definitely a great opportunity. Thanks again. And today I'm going to talk about our you know, toolchain, which is Snapdragon LLVM compiler toolchain. I'm basically the infrastructure lead for the Snapdragon LLVM compiler toolchain. I'm basically positioned here in Austin, and that's about me. And let's move on to the next slide, Nick. Yeah, so today, the agenda is pretty short, right? So we'll only focus on key things in terms of, giving a high-level introduction to Snapdragon LLVM compiler toolchain. And then one of the most important thing that I would like to talk here is staying caught up with upstream. I think many of the speakers before me talked about, staying caught up with upstream. I think there was an interesting talk from Chromium toolchain. There was a talk based on increasing the, or reducing the build time. And there was a lot of talks about, making sure that we're able to distribute in the right way. So those were pretty informative. Some of my, items would be repetitive of what they said. And I'll also talk about the number of challenges that we go through on that front. Next slide, please, Nick. Yeah, so Snapdragon, toolchain, right? LLVM compiler toolchain is basically based on upstream LLVM, toolchain, and we basically distribute this for building Android NDK, and also for images that doesn't have an underlying OS. It actually provides performance and code size advantage specifically for Snapdragon microarchitectures. And we try to, one of the biggest advantage of our toolchain is we try to stay close with the upstream head as well to bring in all the nice features from upstream. We also contribute to upstream. And we also have the toolchain available for both Linux and Windows operating system. So that's a high level, info on Snapdragon LLVM compiler toolchain. I think it's online. You could go search about this, and there's more details about how to download the toolchain. Next slide, please, Nick. So, in the previous slide, I was talking about staying close to upstream head, and I was talking about, hey, that's the biggest item I want to discuss in today's presentation. So here's a slide that talks about, pictorially that talks about how we do that. So upstream, if you see that the top line is representing upstream LLVM project, and the bottom line is our downstream project, LLVM project again. So the red dots that you see on the upstream are like representing commits. Each dot is a commit. And we, as I said, we're trying to stay caught up with upstream. So we're bringing in commits from upstream and merging it downstream because we have target specific implementation as well. So in order to do that, we need to have a continuous way of bringing in commits or patches from upstream to downstream. And it's not that very straightforward to directly take these commits and include it because of number of challenges like others were talking about, right? We take a commit, when we try to apply it on downstream, we're going to have at least 4 possible ways of issues, right? One is like a conflict. You're going to have a conflict when you apply a patch, and that needs to be resolved. And you need to have some resources allocated for that, make sure that that problem is resolved. And then it's also possible that we might run into a build issue, although it applies cleanly. So that's another type of problem. And we might also run into lit test failures, right? So that's another kind of problem. And last but not least, all the checks might go through, but there might be a performance issue, which would be caught, in our performance testing, which like an overnight testing or the next day, right? So these are 4 different possible scenarios that we encounter, bringing in upstream patch. And we also want to stay caught up with upstream because, there is always advantage in being close to the tip of upstream. Having said that, given conflict, build issues, and test issues can block merging the commits, what we do is we use this concept of virtual drain point. So it's nothing but a SHA that we pick from upstream project, and then we decide that, okay, on this SHA, we are going to branch. Any commits before that particular SHA should be inside the branch, and any commits that came outside of that should be reverted. So we're doing out of order merges in our downstream branch. So that's what the bottom line says. And if you see on the right side, you have right side to the green dot. Those are the commits that need to be reverted. Right. So that's about the virtual drain point. Let's move to the next slide, Nick. Thank you. A little bit a deeper dive on how we do that kind of merging, right? So we create the branch, and then now we know, based on a tool that we have, we know, okay, hey, these are the commits that we need to revert because these commits are outside of our window. So we picked up a SHA, anything outside of that window should be reverted. So that's what the VDP Finder tool does. It identifies all the reverts needed, and then we revert the commits on the branch. Right? There is a revert tool which you could just basically go through and use git commands to revert all the commits. And if there's any, it's also possible that while we are doing a revert, some patches might be interdependent, and you might run into some conflicts as well. So we need to resolve all those things on the branch. So once all these issues are resolved, we make sure that we run through thorough verification on Billboard. We use Billboard downstream, similar to what upstream does. We actually go through a rigorous round of verification on that. And then on top of it, we have a number of test cases, obviously, with the resulting artifacts. We run those test cases as well to make sure it meets the correctness and performance needs for a Snapdragon toolchain to be shipped out. So when we do the Billboard verification, it's possible that there might be build failures. Again, you work with respective developers and get the builds going. And finally, we have a clean branch which is caught up with upstream. So that's how we in-house we do this process of staying close with upstream. And there's always a challenge in staying close with upstream. And I would like to talk about that a little bit more in the next slide. The next slide, please, Nick. Thank you. So on the challenges front, right? So earlier, before the mono repo concept came in, we were using this SVN ID in the commit message, and we were able to determine dependencies between commits using that SVN ID. But now with all the single repository concept, that kind of reference to what dependencies we have is kind of gone. That makes it a little harder to determine dependent patches, and everything is in single repository. And as you are most likely aware, based on the previous description that I was giving, we bring commit by commit changes into our downstream. So we actually take a bulk of commits and then try to build it and merge it. And it's possible, it's very much possible that we might not have the right dependencies on top of that, and that could result in build failures or conflicts. So yeah, so with the monorepo concept, that has become a challenge, a little bit of challenge to identify dependencies between patches. And also another challenge, like I think others also talked about it a little bit, we do not know when patches are getting reverted upstream, right? So patches come in, and sometimes it takes a few days, sometimes a week. And if there is a build failure, what we have seen is those gets reverted pretty quickly. But some other performance-related issues, it could take days or weeks, and we and then we would have to spend more time downstream to look into those kind of issues, make sure it is addressed properly. So that's another challenge. And there's also this other type of issues that we have seen in the past where there are CMake changes, and basically that could result in false positive builds, meaning the change comes in, we make the builds, and the artifacts gets generated, and that gets into the toolchain location. But some of the binaries don't really get built, right? So these are they're particularly on Windows. We have seen this kind of issues. It's very rare, but it's still worth to list out here, I thought. And then other thing is the major upstream code changes, right? So that's another disruptive issue that we encounter. When we have a major refactoring upstream, which means that it may not easily apply our build downstream, and then we may not be able to continue with our out of order merges because there is file dependencies with this one or two particular major patches that's worked out. So that's a bigger challenge that we have encountered in terms of staying caught up with upstream. And one other challenge outside of staying close with upstream is we actually use Snapdragon LLVM compiler for our Android builds internally, and there are certain challenges that we face whenever occasionally when a newer Android AOSP drops comes in. oftentimes the version that AOSP compiler uses is different than what we use, and that results in some sort of warnings and build errors. So there's always an in-sync problem between these two compilers, and that's an occasional occurrence. I thought I'll mention it here as well. So these are like at a high level, a number of challenges that we face to actually get in the right set of patches and all the good features from upstream. And distribution-wise, our releases are kind of tied with upstream changes in terms of when upstream releases when upstream makes a major release, and we need to really work through these challenges to meet those timelines. That's at a high level. I thought this will be an interesting information to share with everybody, and also to learn the challenges from others. And I did see, like I said, I did see a number of presentations talking about build time optimization, and those were very interesting, because those are things that we use in our release process as well, right? So we use the Ccache heavily to make sure that the builds, incremental builds at least, happen very quickly. There was one slide, I think that somebody was talking about 5 GB worth of data getting downloaded, and several minutes to compile and all. So the same problems, I think it's interesting to see that. And we use Ccache heavily, and that's how we've been trying to make the build faster. Yeah, so that's pretty much it from my end. If you have any questions on the idea presented here, please reach out to me on the GitHub issue. I'll be available anytime to respond to your queries.
Great. Thank you so much, Sivakumar. I'm so glad we were able to get your talk in and overcome the technical issues together, kind of thing. I think that sometimes some issues just take extra grit, and we got through it, which is awesome. So,
thank you.
So we do have quite a few of our speakers still on the call. I'm just curious if anyone on the live stream has any questions. Maybe thing that might be a little tricky is we have maybe about 30 seconds worth of latency. So by the time I ask this, I probably won't see any responses in the chat for about 30 seconds until plus however long it takes folks to think up questions. So kind of thinking we might skip out on the live questions. I think no matter what, I encourage everyone to go, if you saw a presentation today that was interesting to you, we kind of ran this whole conference out of GitHub, kind of organizationally. And so I've encouraged all the speakers to keep open an individual issue from which they filed their call for papers. And I encourage you to follow up with them on GitHub. That way, bots and archivers can index the page, and we have all that information going forward in the future, because surely we're not the only people that have faced these issues again. And if we had any solutions or know solutions or anything like that, hopefully we can find them again, kind of thing. So not seeing any. Yeah, I think we're just going to skip the live chat. I think there's too much latency. So with that, I guess we'll draw the conference to a close. I totally forgot to thank in the very beginning with all the thank yous. My boss, Steve, helped review and schedule all the talks today. So big thanks to Steve. Again, thanks to Chris and Brittany internally helped me schedule and set up the live stream. I think was really a make or break part of the conference. So really thank you for the last minute help setting all that up. And big thank you especially to all of our presenters today. I'm incredibly proud. It's not quite how I pictured it would have turned out. It was better. So I am over the moon. I think it was great. And, I hope this generally helps people solve problems, or at least put people in contact together, because we don't have to suffer silently alone. We can work together and solve shared issues that we have. And really my hope with this conference is that we can look back on it, hopefully as soon as next year, but maybe a few years out, and kind of laugh and say, hey, yeah, remember all those problems? Those were the bad old days. and hopefully we can solve a lot of the challenges that we still face together as a community. So thank you again, everyone, for your time, and that's the end. So thanks.
Thank you, Nick, for organizing.
Yeah, thank you for organizing it and for coming up with the idea.
Yeah,
y'all can buy me
Thanks so much.
Y'all can buy me a beer sometime, huh?
More than that.
Thank you.
Okay, I'm gonna cut the live stream now. Can we post the slides and links on GitHub? Oh yeah, for sure. So I'm gonna aggressively now go heckle all of our presenters until we have the slides, and then I'm gonna do some post-production and then donate the video clips to the LLVM YouTube channel. And then once those are up and posted, then I will link them from the GitHub. But trust me, I'm very particular about archiving talks and stuff like that. So nothing should go to waste here. Cool. Thanks again for your time, everyone. Take care. Bye.
Bye.